I see people are still coming in, but we can slowly start. So in this welcome word, I would like to welcome everyone. My name is Jakub Szlachetko, and I'm a director of the SOLARIS Synchrotron-Association Center that's located in Krakow. And I would like to welcome two very important persons that will help me to say a welcome word. So Professor Andrii Kordyuk from Kyiv Academic University and also representative of National Academy of Science of Ukraine, with whom we start to collaborate 2 years ago. And I would like also very warmly welcome Professor Britta Redlich, who is a chair of the League of European accelerator-based photon sources and also director of the Felix infrastructure. Felix, which is a FELS for the infrared experiments. And maybe before I will give a welcome word to Alexander and to Britta, I'd like just to say 2 sentences regarding the history of our meetings. And I was just looking on the calendar. So over 2 years ago, during the plenary meeting of the LIPS consortium, we had a presentation of Alexander Kordyuk, who was showing us the research interest of the Ukrainian society. And during that time, LIPS chairs expressed very strong interest to support all actions to help and to consolidate Ukrainian researchers to help them to conduct the science, especially using the large-scale facilities. And during this meeting, actually, SOLARIS has been nominated to coordinate the actions under the LIPS umbrella. And we did organize a year ago the first workshop, start to talk about the research, common research interest. And actually today we have a second workshop that's actually dedicated to talk a little bit about explicitly given infrastructure that can be built within our collaboration, meaning within the LIPS and the Ukrainian researchers collaboration. SOLARIS has a role, and we offer a playground for this collaboration. So we'll see later on this in the presentations. So actually, the workshop is dedicated towards nano and micro X-ray spectroscopy applications, and actually agenda is as following. So, sorry, just had some window. The agenda is as following. So the first, I will present you a little bit the facility, and secondly, Professor Luc Patthey will say a few words about the feasibility study that he performed at SOLARIS when spending his sabbatical during the summer. Later on, we'll have a session dedicated to 3 beamlines that are representative of the type of research we are talking today about, meaning about the nano and micro X-ray spectroscopy. And as a final part of our workshop, we'll see and hear the scientific presentations from the Ukrainian researchers that may use this type of infrastructure. So maybe before the first word I would give to Alexander Kordyuk, just to welcome everyone, and then I will ask you, Britta, to present a little bit what the LIPS is, because it's not necessary everybody here knows about our great consortium. So, Sasha, maybe if you could say a few words, please.
Thank you, Jakub. Thank you for presentation, for starting, and I want to start from thanking to say about for your help to organize us, and now is really it is time that it is much more harder from one point of view for us to do science, to organize, to go to abroad, to Europe, to make experiments. But it is with your help, it seems that it is even more easier than before. And I'm very grateful to LIPS people and for this organization, for separate people, and for Leonid Rivkin and for Britta and for others. And for Solaris people, Jakub made a lot of work to help us. And thank you very much. And I'm looking forward to see the progress of this our I would say most interesting and real project about building of the beamline at Ukrainian Polish beamline at Solaris. So thank you, and let's see what we have now.
Excellent. Thank you very much, Sasha. It's really great to see you as always. And Britta, if I could give you now the mic, asking to welcome and maybe to say a few words about our LEAPS consortium.
Yes, thank you very much, Jakub and Alexander, for having me here. It's a great pleasure to be with you today on this very important occasion of the second workshop for Light for Ukraine. I just managed to flip my background, so I'm really on the page now. Well, I hope this is going to be a very constructive meeting, and I would just like to take the opportunity to introduce you to LEAPS. Jakub already mentioned it. It's a collaboration of our synchrotrons and free electron lasers. And if I can manage, I would like to share a few slides just to introduce you what LEAPS is and what we are doing with LEAPS and why initiatives like Light for Ukraine are so much at our heart and get our strongest support. So LEAPS is a consortium of synchrotrons and free electron lasers, as you all may know. It's the largest analytical facility network worldwide, and we are trying to expand our interdisciplinary user community. As you see on my screen, this comprises 19 synchrotrons and free electron lasers in, at the moment, 16 institutions and 10 countries. So we hope to expand, but that's what LEAPS is at the moment. It provides more than 300 operating end stations to a very large user community of more than 35,000 users. And you see the other key figures over here, probably the most prominent one being the more than 1 million beam hours per year that go to users from the facilities that you see also in the picture. Furthermore, we, of course, have the synchrotrons, and prominently on the high energy side, you see ESRF and Petra 3 to the mid energy range, a number of synchrotrons. And then on the lower energy end, we see Solaris, of course, which you're very much familiar with. From the synchrotrons to the free electron lasers, again, we span a huge frequency range, and you see the flagship installation of the European XFEL ranging to the lower energy branches with Felbe in Dresden and Felix in the Netherlands. So this covers a lot of experimental opportunities and possibilities, and we associate within LEAPS to partners, as we see. Most prominently, probably one of our associates is the European Synchrotron User Organization, so it's very important to us to connect to our users, and this is a way how we do that. But also Sesame, the synchrotron in Jordan, is an associate partner to us, and we support very much activities going on there. Well, if we then take a look at activities very briefly and in a nutshell, it's very important, of course, that we do activities together. So there's a whole range of projects that are going on within LEAPS that we do together. And I don't want to go into any detail, but you see there's a number of ongoing projects. Projects are granted, and I prominently would like to mention the Nephews kickoff meeting, which will take at Solaris. Solaris is really in the lead for this project and has done tremendous work to get Nephews project started. Kickoff will take place in February, and there are proposals under preparation that we do at the moment. Important for us is also that we have conferences that we organize where we meet the user community. So there has been the Life Science Conference last year, and the next user meeting will be organized in spring 2025. So we hope some of you will be able to join us there. Finally, the hard work is done within LEAPS in the working groups, and I think you will see the output of that also when you look at the beamline that will be built at Solaris. So the Research and Development Board organizes a number of work packages crossing the technology work package from beamline technology and source development, components about data, and also has complementary working groups carried for industry uses, education, and training. And importantly, LEAPS also comprises strategy groups, the SG1 and 2, caring about synchrotrons and free electrons. This is really extremely important when it comes to projects that we want to do, and all our developments are safeguarded in these working groups, and you see a huge number of experts who engage there. Let me also tell you that LEAPS has some key activities in lobbying for the Commission to get visibility. And we have recently had 2 lobbying events taking place in Lund and importantly in November in Strasbourg to see how much we can make a prominent role for FELS and synchrotron science, especially at the Commission level. And Alexander joined us in Strasbourg. We were very happy to welcome him there on the panel. A great occasion to meet and engage again. So, of course, we want to continue that, and LEAPS hopefully will become a legal entity in 2024 so that we can also speak with one voice on behalf of the whole community. And well, our vision and activities, if you are interested, there's a number of papers where you can see what LEAPS cares about, how the landscape is organized, and what is the strategy. They are all on our website. And I think some of the documents at the moment, so the position paper and the missions, but also our strategy document show how much united the facilities are at the moment. There's a common roadmap approach which really guides the future of these facilities in Europe. And of course, part of this is that we worked collectively on innovation and technology. We care about technological sovereignty and the European cohesion so that we want free access for all academic users, safeguarded on the level. We have very much heart for training and education, but importantly for this meeting, the European science diplomacy, and that bridges very nicely to where we are today. Jakub already alluded. It is 2 years that we took the initiative. I think wholeheartedly all the LEAPS participants really immediately engaged in this activity. The fantastic workshop that took place less than a year ago with 250 partners really, or participants really showed that we should on the right path and should continue. We are very grateful to SOLARIS National Synchrotron Center that they are coordinating and implementing this at the moment. And I think I can only wish you all the best for the meeting today. We are very much looking forward to the outcome of the meeting. We are excited to see that there's a planned synchrotron beamline that will take lead at SOLARIS and focusing on this important topic that you together, and this is important, together decided to work along. So I'm very excited to see that and looking forward to hear more about during the meeting today. That's all I wanted to share with you at the moment. Wish you all success. And Jakub, please take over again.
Thank you very much, Britta, for the presentations, for introduction. And yeah, I mean, I should probably pay attention or say that people that participating in this workshop by make a warning a little bit, you know, gentlemen, ladies and gentlemen, by taking a collaboration with us, you will become a part of all what Britta showed. So all the activities, you are really welcome to join us and to be on board, to be on the LEAPS board. And as you may see, we have a lot of different activities, and I'm sure everyone can find his place and take some tasks within our collaboration. So thank you very much, Britta. And yes, so I think welcoming is over. Now it's time for the hard work. And now we'll make 2 presentations. So first, I will show you a little bit the current status of the SOLARIS. I will focus explicitly on the infrastructure. Okay, so there will be no talk about the science. And actually, my presentation is just the introduction to very important presentation, which will be after by Professor Luc Patthey from the Polsher Institute, who will present his results of his 3-month sabbatical stay at SOLARIS. and the studies of possibilities of implementation dedicated infrastructure at the SOLARIS infrastructure dedicated or to be used by the Ukrainian society. All right, so go to my presentation. Just let me share the screen. Yes, this should do. So now I will need this one and this one. Yep. Okay, excellent. So I hope you do see slides and you do see my laser pointer. So that's right. Can I just get the confirmation? Sometimes I'm getting lost with I have two screens. So do you see?
Yes, we do. Yes,
excellent.
We do.
Thank you very much. All right. So with this presentation, I would just to say a little bit about the SOLARIS infrastructure and just to say you what actually infrastructure status we have. So SOLARIS is located in Krakow. It's actually still within the city premises, very close to the new campus of the Jagiellonian University, which is up here on this photograph. And actually on this campus, we have really over few hundreds of scientists working in the Faculty of Chemistry, Faculty of Physics, Faculty of Biology. We have also Małopolska Center of Biotechnology, so very strong scientific community located next to our facility. This has been already mentioned. We are a partner, or we are complementing family. We call it Family Lips Family. We are 16 facilities, as already introduced by Britta. And just the two slides about the accelerators. This has been already mentioned. The SOLARIS is a low energy ring. I'm not going to talk about the details here. It's just to say that we are operating two accelerators. So we have a linear accelerator that gives us the 600 MeV electrons. These electrons get injected into the storage ring, where they get the final energy of 1.5 giga electron volts. So actually, what you have here is a photograph of our ring from the top when the concrete is removed. And actually, maybe what's the most important to remember, or the numbers that are particular for SOLARIS, is the ring circumference of 96 meters. Electron energy is 1.5 giga electron volt. And we have so-called 12-fold geometry, meaning that the full cycle is made with the 12 bending magnets that are located in the storage ring. Of course, we are still using insertion devices for production of X-rays on the straight section. Now, regarding the infrastructure, actually now we have 7 beamlines into operation. I will say in the next slide more technical specifications what these beamlines can do. This is just the general view of how these beamlines are located around the storage ring. So we have on this side, we have a low energy X-ray beamlines, so soft X-ray beamlines or VUV beamlines. On this side, we have two beamlines that are operating the hard X-ray energy range, and the series beamline that's dedicated to IR spectroscopy. Now, maybe one comment regarding the naming. I'm sure everybody knows, but just wanted to emphasize that the names of SOLARIS, it's not connected with the bus factory. Okay, so if somebody missed that, I would like to pay attention that the SOLARIS, it's not connected to the bus factory, but it's connected to Stanisław Lem, who was a great Polish writer about the science fiction essays, and he wrote this excellent novel called SOLARIS, which was translated to over 50 languages worldwide. There were several movies recorded. And actually, having a facility name as SOLARIS, the naming for the beamlines, we try to keep the nomenclature, meaning the acronyms are related to the science fiction area. So, for example, you may see a Pirx beamline that actually comes from the tales of the Pirx pilot, and everybody knows that the Pirx was flying to the Astra planet and so on. So we try to keep these nomenclatures just to be consistent. So we are operating around the science fiction area. So this is, Alexander, already a big challenge for you, because you have to write the proper name for the new infrastructure that eventually will come. For example, also we are not stick explicitly to the Lem, to Stanisław Lem, because it's difficult to find all the names from his books, but we keep this science fiction area. And for example, the Siri beamline, this is something from the modern times, but you may know this is character from the Witcher, Polish Wiedźmin, a series of fantasy novels that gives the name for the chemical imaging at the IR range. All right, so this is the actual status. Now, we do have 4 big investment projects that are coming in. So we have actually 4 stations or 2 beamlines and 2 stations that are being built right now. So we have SMAUG and the SOLCRIS beamlines, so the small angle scattering and the crystallography beamlines that are going to be built next 2-3 years. We are building a NAP-XPS branch beamline around the soft X-ray energy range, and simultaneously we are also constructing an operando end station that will allow you to look on the materials at the heart X-ray energies and to look into the materials at operating conditions. We do have some projects submitted for the applications, and now coming to the heart of our workshop today, there is a place of the sector on the sector 2 on the straight section where we can construct or we can envision a beamline that is built within the LIPS initiative for the Ukraine. So this is a beamline that where the Ukraine can consolidate their research. And this will come, of course, later a little bit more in details with the Luc Patthey presentation. Now, just to mention, we do have on our facility also the cryomicroscope center. We operate 2 cryomicroscopes, and we do operate, or we start to operate or bring into operation the neutron laboratory. Actually, the source, the neutron source, it's coming from the Kyiv. So this is a collaboration between the Faculty of Physics and the Solaris. So we do have already some Ukrainian accents here. And just to say, this portfolio of the beamlines of the infrastructure is to be widely used by the researchers. So when you think of your projects, you don't have to focus on the single beamline. You can still think to use the other beamlines for your research projects. Now, very briefly, I'm not gonna go into details, but just to, this sets a background why we talk today about a little bit micro and nano tomography. So actually what we do operate right now, we do operate a range of the soft X-ray beamlines that provides either the spectroscopic applications, the microscopic applications, but at the soft X-ray energies, but also we do have 2 beamlines which are very complementary when we talk about the angle resolve photoelectron spectroscopy. So this is already available now on the Solaris. And what I mentioned, we are building the NAP-XPS station that is dedicated actually to the XPS research at ambient pressure, also working on the soft X-ray energy range. On the hard X-ray side, we do have 2 beamlines that are operational. 1 beamline dedicated to the spectroscopic application, and the second beamline dedicated to microspectroscopic applications, but at the hard X-ray energy range. And then we have these 2 beamlines and 1 end station that are coming into operation. So the beamlines that are dedicated to the structural research, and the beamline dedicated to the chemistry application. And on top of that, we do have an IR beamline that is operational and offers 3 end stations for researchers. And then we have the cryomicroscopes that are available also for the users. So this is the portfolio. And when we make the discussions with Luc Patthey, with Alexander, when we look on the portfolio of the methods that we have actually on the synchrotron, we found out that's what we are missing, and where is the power of the Solaris is the nano-spectroscopy or the microspectroscopy at tender X-ray energy range. As we all know, this range, it's not really well explored. It's a little bit difficult to be explored because you need a little bit of vacuum conditions. You can work purely in the ambient environment. So it's technically challenging, but on the other hand, it offers great opportunities, and the research on the materials, like which are very important for many research fields, like sulfur, phosphorus, potassium, and so on. So this is where we got. So we try to have at the Solaris a range of the methods that provides the scientists research, complementary research in different research areas. Actually, what we intend to offer, it's not particularly different to the other synchrotrons. I think every synchrotrons at the end has very similar portfolio of research methods, but actually where we get and what we found, it's really missing. It's a dedicated nano-spectroscopy beamline that can be built within our collaboration within the LIBS or under the LIBS umbrella. And this could be called Ukrainian beamlines, actually, at Solaris, built within our consortium. We don't have, for the moment, a concept. We don't have a funds yet, but this, I think, we can organize. We do have some very nice, maybe not yet decide or not yet finalized in-kind contributions, but we think that Polshar Institute, at least, there are signals we'll see from Luc Patthey how far it gets. We have a signals that some of the equipment can be already donated for the beamline. The rest, of course, we can find through all the projects or to joining the projects that Britta mentioned. There is so many activities that I'm sure we can find the dedicated funds to complement this project. So with that, I would like to finish. I would like to thank you for your attention and very smoothly move to presentation or Luc Patthey. I would like to welcome Luc. I'm sure Luc is with us, and I saw him logging in. Luc, can we see you? Can we hear you?
Yes, I can hear you. Do you hear me?
We do hear you. Great to hear you.
Okay. Yeah.
We can't see you yet, but I'm sure this will come.
I have my camera on.
Okay.
It was fine.
Okay.
I see myself.
Okay, good. So this is coming. Hello, Luc. Great to see you. Great to see you. Thank you for joining us. Thank you for being here. So I try to make a short introduction. Actually, you are the, I would say, VIP of today's meeting. So you are the person that will introduce a little bit more into where we get, and you will say us a little bit the status of your work, actually, which I think is really excellent. So yeah, the microphone is yours. Thank you.
Hello, everybody. First, I would like to thank again Jakub and Alex and Britta to give me the chance to present what I very much enjoy to do during my few months or 2 months or 3 months of sabbatical in summer 2023 last year at Solaris. I really enjoyed these times. It was a great pleasure to work with all the teams, to see actually people very strongly motivating and of course trying to move a little bit toward this fantastic project, which is Light for Ukrainian. So it's really my pleasure. And thank you, Jakub, for all the introductions. I hope I will be able to present you all you promised to the audience. I will try my best. So I will share my screens. Just a moment. Even after 3 years of Zoom, it's always an issue. So here, share. You should be able to see my screen now.
Yeah, we do see. It's still not yet.
No, I'm coming. I just have to. Voila.
Yeah,
good.
Excellent. Looks great.
Good. So you should see my laser as well.
Yes.
Good. So I will try to show you some kind of technical feasibility of beamlines which could be built at Solaris. So my name is Luc Patthey, and I'm working at PSI for a few decades now, and I'm leading the laboratory for advanced spectroscopy and X-ray source. And this is really my pleasure to show you what I try to do during these times. So I'm really pleased and also PSI can contribute to this fantastic project beside Solaris and our colleague from Ukrainian, from Kyiv, and also with actually the LIPS. And what I will try to do is to talk about the transfer of a so-called ondulator U19s, which is existing now at and serving SLS light source at PSI for many years, and to move this ondulator to Solaris. And the goal is actually to generate X-ray source in the tender range up to the 8 kilovolt by using an in-vacuum insertion device. And we have been working fantastically in collaboration with the Solaris groups to check the compatibility and the performance of these machines. We are now, or at least I'm now very convinced this will be a very nice move. And I will try to just shine few slides on the potential optical layout of a possible beamlines from micro or nano XAS. Okay, but to also tell actually people that Switzerland is extremely supportive with this project of Light of Ukrainians. I have the full support from PSI, from our director, the division's head, Director Christian Rueg, the division head, Gabriele Eppli, and also the vice formal President Leni Rivkins, who is very active with me on this project at PSI, also Hans Braun. And actually supporting Ukrainians is actually also part of our website, as you can see it here. And not only PSI, but we had recently a very excellent good news. We get granted for $500,000 last December from the Swiss Secretary of Education and Research and Innovation, the SERI, to finance 3 years positions for postdoc, and also to invest some money for this project. So you see then this is not just my initiative, this is not just PSI initiative, this is not, we are fully support. Also, we have a strong support by the Swiss authorities, and with our colleagues from Ukrainians, we have been submitted also a project at the Swiss National Foundations. And from my side, I'm still waiting for the output of this project. And last but not least, there is many different initiatives and discussions at the ETH domains to support this project. So everything's actually from my side start from then we will actually build upgrade the SLS to SLS2, and by saying so, we want to increase the brilliance of these machines. But by doing that, actually, we have a lot of insertion device which becomes available for this project, and the idea was, why not to move one of those insertion devices to Solaris. We have now actually started this actually very very challenging journey by actually entering the dark periods, where we have to rebuild this year the rings and be in user operation in 2025. So we have also internal very high constraints in terms of beam times. But the dark times from SLS, as you can see, has started in October. You see the rings, and now few days or two weeks later, the ring is completely empty. This is pretty impressive by the people from done here at PSI. And what is important is, as I said, we have a zoo of ondulator which becomes available, and I will focus on this one, the U19s. We have actually, which can be actually suitable for these beamlines, but we have a bunch of other insertion device, and we have 3 other units of U90, which is, I would say, just for sale. If somebody wants to look, please look to eBay, and maybe you can find something to buy like this. Basically, this U19 has been removed from the tunnels in October 25. Here you see it the day before, it's still in the tunnels. It's already flying in 25 over the tunnels, and now since 2020, the 26th of October, is actually in the storage place, waiting for his future life at Solaris. So what we want to do, as already mentioned by Jakub, we would like to build a beamlines, which will be on the sector 2. And this sector 2 has a very interesting feature. Then actually it can build, we have rooms for about 33 to 34 meter beamlines, which will be located in the new external hall, which is actually a perfect location for this kind of nano or microXAS beamlines. And the goal, first you have to see if the piano fits the rooms. So with the help of the engineer from Solaris, we pick up the CAD drawings of these machines. By knowing the beam height is different at Solaris than at SLS. We have at SLS a beamline of 1,400. We have a space which is actually given between the valves, upstream and downstreams. And with the help of this, the teams of Solaris, at least we already virtually managed to put this device in the sector 2. So it's not yet, it's still science fiction, but I think it's going in the correct way. And we fit, these machines fit the rings. So I think we have very good, we can be very confident that these machines will be installed at Solaris. Now the next step is to see what these machines can actually provide by knowing that this ondulator has to work on a 1.5 GeV, and it's a different rings, and it's an in-vacuum insertion device, which is completely, I will say, unusual to build that kind of insertion device at a low energy machine. So we tried to do our homework, and we had the first curved, giving flux in terms of function of intensity, in functions of energy, photon energy, and it was actually extremely promising, where we can deliver fairly decent flux up to 10,000, let's say 10,000 kiloelectron, 10,000 eV. So we continue the journey of implementing, looking the technical feasibility. By looking also, as Jakub mentions, that will actually cover a very interesting science, which is actually halfway between two domains, which is done by Swissfel, SLS here in the soft X-ray and hard X-ray. This is actually a portfolio of science we have at SLS too. So I think these machines will actually nicely serve also the chemistry imagings and having also some spectroscopy. I think it's a very good move to actually will be unique feature from Solaris. Now we had actually working a little bit more in details on what the technical situation will be. And we have been facing to reality in the sense that you see here the K scans, so the energy scans you can provide with these machines, moving from the 1st to the 15th harmonics. And you see, as function of the minimum gap you can achieve, you will be in principle nicely move up to the lines here from one harmonic to another. However, we have to face to reality. These low energy machines has a minimum gap currently at 7 millimeter. So that means all this part will be difficult to achieve. So we will just be stick to these dark blue lines. And as you can see, we have actually by this, you have actually energy gap here between the 1st and the 3rd harmonics, between the 5th and the 7th harmonic, between the 3rd and the 5th harmonics. And also you have weak intensity to higher energy. And this could be actually a big problems for X-ray absorption spectroscopy, which are interesting to important K-edge and L-edge of elements. So we have been scraping our heads how to solve these problems. Of course, the easy case will be to reduce the gaps, but this is actually not that trivial on this kind of machines. But we come to the idea actually to use not just the odd, but also the even harmonics, which is actually pretty weird ondulator beam lines. But it turned out with this machine, it's completely possible to do that. And I will try to motivate this, this approach. Here you see, so to say, a gap scan. And you see then if I move from the third to the fourth, fifth, and so on, I can continuously follow actually the energy. I have no more energy gap in my spectra. And we have, that will be actually a pretty nice solutions for SOLARIS. However, we have to understand why people have been not doing that in the past, and we will be the first to base the beamlines using the even harmonics, is actually just because of the excellent matchings of the natural emittance of this SOLARIS. I will try here on to explain you a little bit in detail, more in details. If I'm focused here on the 10th harmonics, you have the maximum peak, intensity peak here, which correspond here to the blue edge, but you have also on axis the redshift, which actually has a little bit less intensity. And if I look the shape of the radiations, which is emitted from the blue to the redshift, it's a nice cones. Even for the even harmonics, and you start to see something weird splitting here of the conus, which is completely normal for the even harmonics. But this is at this normal nominal natural emittance, not yet a big deal for the beamlines. However, this will become an issue if we will have actually a 5 times better natural emittance at SOLARIS, which is not the case, because you see here the same picture, I start to have a very weird beam distributions, which can be barely used by the beamlines. And if I go in the other directions, let's say at emittance, I have here somebody who asked to come, but sorry. If I have a bed emittance, I will have actually for all the way from the red to the blue edge, something very Gaussian, but a big potatoes, and I will lose a lot of photons because most of the photons cannot be served to the beamlines and be introduced to the beamlines. So in other words, the emittance of SOLARIS is a perfect match to this U19 to be used at odd and even harmonics. And we try to better to understand that. And you see here, everything will go through the beamline. So even if you start with even and odd harmonics from the 2nd to the 8th or even to the 15th harmonics, everything looks pretty good for this insertion device. And the source size will be also very close to the electrons beam size, which is 180 microns horizontal and 11 microns in the vertical size. So I think we have all the ingredients here with the U19s to start to work on the beams. And from SLS, we have also a couple of hardware from different beamlines, which will hopefully become free to be recycled. I will say this is just a list of equipment we could potentially use also for these beamlines. This is just a list. There is no decisions yet on what can be and what will be recycled, but it's actually something that I will to discuss with my colleagues in the next months. But a very nice layout of beamlines, which is already has been used for many years at SLS, is the microXAS beamlines, which actually are very nice designs. It's actually use first collimating mirrors to have collimations in the verticals and use a double crystal monochromator with the KBs. And I think this kind we can inspire ourselves for these beamlines, for SOLARIS with these beamlines. And if you see at SLS, we have a beamlines of 440 meters, but the source from the distance from the source, the first mirror of 20 meters. In case of SOLARIS, it will be 12. So it will be a perfect match with beamlines of 34 meters. So I think with next steps will be actually to investigate the layout of the optics. With that, in conclusion, I will say the U19 will fit to SOLARIS. It will deliver potent quality of high quality up to 8K, and it matches the natural emittance to use event harmonics and to do gapless energy scans, which is mandatory for microXAS beamlines. And actually, the source size is also compatible for future developments of beamlines for microfocus. And I'd like to thank everybody who has been involved on this study, people from SOLARIS, also for my colleagues in Ukrainians, and also the strong support from PSI, without forgetting actually the financings from the Swiss state and the Swiss National Foundation. With that, I thank you everybody for your times. So I'm open for questions, if still questions we have.
Thank you, Luc, very much for very nice presentation and summary of what have happened last month. It's really the photographs from the rings from the SLS ring are extremely impressive, I have to say. I should maybe emphasize before we'll get to the questions that I should emphasize that simultaneously to all the work we did on the infrastructure, we did also research on the interest of the Ukrainian researchers. We made a survey. We tried to research a little bit to match up with the beamline, and actually this very well matches to the possibility of the beamlines that the area of the micro and nano X-ray spectroscopy is of big interest of the Ukrainian community. Mm-hmm. So this matches really, really nicely with the project. And it's why actually we have all the scientific talks in the early afternoon dedicated to this research area. I just, first question, I mean, is the logotype of PSI somehow new, or is just for the dark period? Is just for the dark period, or?
No. This is a new branding, so it's a completely new. So I didn't want to stress too much, but it took me half a day to upgrade all my presentation with a new PSI logo, which I'm very pleased that we saw the new logo. This is the official one.
Okay. Yeah, I mean, being many years there, I mean, I was a little bit surprised. It's like, with that change, which is very nice, I must say.
So even if you see, if you believe things doesn't move, it's moving at PSI.
Excellent. All right. Are there any questions from the audience regarding the Luc's presentation? Somebody wants to comment? I see Alexander put his mic on.
If there is no question, maybe just we have time. I wanted to ask before, actually, how you estimate how this switching between harmonics happens during experiment in this undulator? Could you comment on it?
That will be actually, there is no difference switching the harmonics between the even harmonics when we do that regularly to move the harmonics from one harmonics to another in experiments. So this will be no big difference switching from the even to odd harmonics. What I think will be important is when you do a scan, energy scan, you should possibly stay in the same harmonics, because you will have problems of stitching. The flux will be not completely different. Maybe the heat load on the optics will be slightly different. So I will strongly recommend to find to make a compromise, or to find on which harmonics you will do the experiment. But from the technical point of view, it's you change the gap according the mappings where you want to go on the defined harmonics. So I see no big difficulties here.
Yeah, that was the question about experience in PSI, whether there is synchronization between monochromator and undulator for such a long energy sweep.
So I think scanning the monochromator and the gap of the insertion device we do that routinely in the routine manner. That's not a problem. We even do that at the Swiss FEL, where you have not one ondulator, you have 18 ondulators to scan at the same time at the monochromator, and even phase match between the insertion device. So I see there are no problems. But I will say again, during energy scan to make your edge spectra, absorption edge, I think it will be good to stay in the same harmonics, either even or odd.
Okay, thank you.
Thank you very much. I see a raised hand from Vitaly. Vitaly, please put your mic on. We still...
I don't hear anything, but...
Hear me also.
Okay.
This is the hand, but Vitaly Mikhailik,
yeah, Vitaly Mikhailik. Can you put your mic on if you want to ask a question? Maybe has some technical problems. If something can be asked later on. Okay, I mean, we are extremely perfect on time. I would like to thank, first of all, again, Professor Britta Redlich, chair of LIPS, to introduce us to the LIPS world. Thank you to Luc, thank you to you, Alexander. And yeah, we start at 11. We'll hear 3 presentations from I think, the representative beamlines in this micro and nano spectroscopy world. So really looking forward to the next session. So we have now time for short coffee, and we meet again at 11. Thank you very much.
Thank you. Coffee break, guys.
Thank you. Right. So having a Swiss ondulator in mind, we should start exactly at 11:00. So welcome everyone back. So there are 2 things before we'll move to the presentation. So first, I've get notice from Luc that he got a question via chat. So maybe if Luc, you could tell us the question and eventually respond or make a comment.
Okay. Yes, the question is serving the energy range from 1 to 8 kiloelectron volt is actually limits their experiment to vacuum experiment, and this is a question if we can actually, if this is the case or not. And I would say yes, from the up to the last mirrors, everything has to be perfectly in vacuums. But I would say this is more designs of the future end station, which is I do understand not at all discussed so far, but I would say there is few options worldwide or solution worldwide to actually to move from UHV to near ambient pressure experiment. So I think this is if this has to be discussed, that will be today the good place if there is a need on these directions.
Exactly. Thank you very much. I think this will be addressed a little bit in the presentation of Marin Cotte, who will present ID21, which I had the pleasure to work there for 3 years, and I think it covers closely the energy range we are talking about also. So I think, yeah, the challenge is that we have to cover a little bit the vacuum conditions, but I think we can work partially with helium environments and so on. So yeah, we'll see that this can be up to discussed. So before I will start the session, I just wanted to share with you one slide just to show you. So here, what you see is the result of our survey we did with the Ukrainian researchers, just to confirm an interest of or research interest on eventual X-ray research with the synchrotrons. And as you may see, indeed, this nano and microspectroscopy beamline, maybe it wasn't great majority, but it showed its great interest from the Ukrainian community. Therefore, I think the combination of what's possible, what's available, what's offered by SLS and the interest. I think is a great coincidence to do the work and to work around this area. All right, so now I will give a voice first to Eva Partyka-Jankowska, who will chair this session. Eva is our coordinator for the X-ray spectroscopy beamline. So Eva, take a mic and give the introductions to the speaker. Thank you.
So, Jakub, thank you very much for the kind introduction. And maybe I will just give you a word of explanation, because actually this session was supposed to be led by Anna Wach, who is one of the organizers of this workshop. But unfortunately, due to the health reasons, he cannot join us today, and I will lead the session in her place. So in this session, we will have 4 presentations. The first part consists of 3 talks, and we will get an overview of research potential of nano and micro X-ray spectroscopy beamlines. And this part will be followed by a talk with the aim to provide us with some information on Ukrainian synchrotron-association. So maybe one remark concerning the questions. So we have 2 options how to ask a question. So just wait until the end of presentation and ask the question, or you can write a question in a chat anytime you like. And afterwards, I'm going to read all the questions if we have enough time. If not, I will ask the speaker to answer the question. So let's start. So the first presentation will be given by Małgorzata Makowska, who is beamline scientist at microXAS beamline at Swiss Light Source, and also material scientist at Advanced Nuclear Materials Group at Paul Scherrer Institute in Switzerland. So, and the title of her presentation is Chemical Imaging and at the microXAS beamline and Plans for the Bright Future at microXAS 2. So Małgorzata, the stage is yours.
Okay, thank you. And first of all, thank you for the invitation for inviting me here. So let me just share the screen. So again, also in my case, can you confirm that you see the presentation mode?
Yes, yes, we can see your presentation.
Okay, so thank you again. That's one of rare occasions when I don't need to repeat my name. So thank you for that, for the introduction. So yeah, I will present you some selected, a little bit description of our beamline microXAS, which is located at SLS, Swiss Light Source here, as you see on the picture. And but I will focus also on scientific cases that we covered during last years. And then I will tell you also about our plans about the upgrade of the beamline, so new possibilities for the future. So our team, so this is our team, the beamline. We are 3 beamline scientists. Daniel Grodimont is our group leader. Then the second scientist is Dario and me, myself. We have a great support of 2 technicians, Beat and Mario, and we have 1 postdoc currently working with us. So, as I said, I will introduce you a little bit the beamline layout, and then I will focus on some examples of science cases that we tackle. So these are actually 4 main, most frequent scientific directions that we work on recently, but also that we aim to force in the future forward. So I will show you some examples about radioactive materials, because here I would like to mention that microXAS is the only beamline that at SLS, at the synchrotron, that has a license for studies of radioactive materials. And then we also measure some biological samples. We do quite a lot of studies on electrochemical devices like lithium-ion batteries or other types of batteries, but also electrochemical cells like fuel cells or electrolysis cells. And since a couple of years, we spent a lot of time also on experiments on advanced manufacturing, in particular additive manufacturing with lasers, but it's a bit broader than just 3D printing. And as I said, I will introduce you plans for the future. And in the end, if I still have time, I would also like to give some examples from Phoenix beamline, which is actually maybe a more interesting case as microXAS is operating at a bit higher energies usually than we are discussing today. And Phoenix fits a bit better. So our main, the main goal or activity at microXAS beamline is chemical imaging, and that's also how we call our group. It's a chemical imaging group. So what is the difference between physical imaging and chemical imaging? So physical imaging, that's at least our understanding of it. This is imaging that gives you information mainly about morphology, structure, and it's with X-rays, it's typically based on absorption contrast and phase contrast. What we do at microXAS, we provide the images so we can see structures with spatial resolution based on a chemical contrast, so chemical composition. We can see distribution of different elements, but also with spatial resolution, we can visualize speciation of or chemical states of specific elements. And here is an example, that's our example case, what we did. So this is an image done with optical microscope and with SEM of some kind of writing. And this is an example of physical imaging where you see the morphology, the surface structure. But if you do the chemical imaging, then you can kind of deconvolute the information there. And this is, of course, an example of fluorescence contrast mapping, where we could see that the fluorescence of silver and fluorescence of gold gave us a different image, and we could read what's written. So the beamline, as it was in the past up to last October, looked a little bit like this. So this is a simplified sketch of the beamline. So our source was undulator U19. So one of these undulators that Luc was talking about, that perhaps will travel to Poland, perhaps the other one. Then in the optical hatch, the two main components were one mirror, which a dynamic focus in one direction and collimation option in other direction. Then we had the fixed exit monochromator, and in the hatch, experimental hatch, we still have two sets of KB mirrors for two different sizes of focus. So we could operate with focusing at around 10 microns or at 1 micron. And at the second station where we would get this 1 micron, we would lose a little bit of flux because of the acceptance of the mirrors. And then also we had options to do the focus with gratings, but also sometimes we used the full field microscope, so we could actually use perform the full field imaging and relatively easily switch between focused beam and parallel beam, collimated beam for the full field imaging. So that was quite an interesting and unique option. So up to now, we were operating in this range of energy from 3 to 22 kVs. However, in reality, it was rather between 4 and 20. So that was like a reusable flux. At the edges, we had very few photons. And this is a sketch of how the final sample position looks like. So we had always a manipulator. So that would be a case for some ex situ experiments where we have a manipulator for the sample, which can be moved, which can move a sample in all the direction, X, Y, Z, also with a rotation and with a swivel. So we could also correct for the alignment. Simultaneously, we were able to measure fluorescence and diffraction from the sample during the scanning over the sample, and also transmission signal through the sample. So these three signals we could measure at the same time using monochromatic beam. And of course, another type of measurement that we used to do as a standard measurement was absorption spectroscopy, XANES or EXAFs. But then this, of course, had to be done with energy scan, so not simultaneously with the others. But it could be done at the same sample after selecting a specific point, for instance, based on diffraction and fluorescence images. So now I will present you some science cases. So as you heard, as I was introduced by Eva, she mentioned that I also work in the nuclear materials group. So several examples I will present you from this field. So what are the challenges in nuclear fission reactors? So here we have the challenges that we tackle at microXAS. So this is maybe something new for you, new field. So this image shows a pellet of spent nuclear fuel. So this is essentially uranium oxide embedded or placed in a cladding made of zircaloy. So here we have, during the operation of the reactor, we observe a number of structural changes inside the pellet, inside the uranium oxide, but also we have precipitation of hydrides and zircaloy claddings. We have oxide formation at both edges of both sides of the cladding, and all these phenomena. Yeah, then also we can have some deposition from the cooling water on the cladding, and all these phenomena can lead potentially. I mean, we prevent it, but they can lead to some failures that we need to understand well to prevent them. So what we do at PSI, we have a special FIB, which is placed in a hot lab. So it's a FIB that can also produce small, tiny samples from highly radioactive materials. And then such sample, so we can extract a pillar even from a spent fuel, which is itself very highly active. But when we downsize the sample, then the activity is not so high. And actually, we could even bring it to different beamlines, those which do not have the license for dealing with radioactive materials. And then such pillar, we could place at the sample stage, sample manipulator of the microXAS and measure different things. So here's, I would like to actually start with the 2D imaging. So this is a thin lamella also extracted using the FIB of the cladding of the zircaloy, and for which case we performed 2D imaging. So we were scanning in 2D over the area around the crack. So this is this crack in the zircaloy. So this is this zircaloy cladding and on purpose induced crack. And we were studying the distribution of hydrides. So here we could perform this mapping of different types of hydrides. We actually could notice that we have, so based on diffraction contrast, we could see that we have two different types of hydrides, which was before not clear if one of them is actually stable. People believe that it's metastable, but actually we can see that it stays in the structure. We could also, based on fluorescence, see differences between two different parts of the alloy. I am not going into very details of it, but so here we could see that we have two different alloys, and the difference we could see essentially based on fluorescence and diffraction contrast. And thanks to this, we could see that at the edge of these two alloys, we have formation of hydrides in the high concentration. So we could see that these hydrides are agglomerated at this edge, but also at the tip of the crack. So the interesting thing is that the stress induces formation of the hydrides. And then on the other hand, the hydrides are very brittle. So then which accelerates the formation of the crack itself. So then before I move forward to the next case, I would like to say something about the 3D imaging. So, because this is actually a direction where microXAS, where our beamline is going towards 3D or even 4D imaging. So 4D meaning a time resolved. So we can do these experiments that I presented already. These types of experiments we can do also in 3D. That means that we can scan the sample in X and Y and also rotate. And then for each, and this is an example of scanning for tomographic slice, for obtaining a tomographic slice in such a pillar. So we scan the sample in X and we rotate the sample. And then for each pixel, essentially, we get the spectra. So in this case, fluorescence spectra for each pixel. And for each rotation, again, another one and another one. From this signal, for each energy bin, we can construct sinograms. And then using tomographic reconstruction algorithms, we can obtain fluorescence contrast images for each energy. And based on this, we can map, and of course, this we can do for several slices or many of them, and then finally obtain the 3D image. If we do it with diffraction, we of course first we do, measure diffraction rings to the images of diffraction rings, which first we need to azimuthally integrate. And then the further procedure is the same. So based on the patterns which we have to, for each measured pixel, we construct sinograms, then we perform tomographic reconstruction, and then we have we can have a 3D image of crystalline phase distribution. And here is an example, again, from spent nuclear fuel. And this is actually what you see here is actually a high resolution imaging based on attenuation. Actually, this one is on phase contrast, but we also have it based on attenuation. So this is a result of tachography performed at CSAC's beamline. And you see that these are two pillars extracted from different parts of the nuclear fuel, spent nuclear fuel. And in this signal, with very high resolution, we could see that we have some inclusions inside or pores or whatever they are. Yeah. However, from this contrast, we couldn't see, we couldn't say what are they. Yeah, we couldn't even say if they were really pores or filled with something. And what we did, we took the same sample to microXAS, and we performed this tomographic microscopy based on fluorescence contrast, but also on diffraction contrast. And then we could match exactly same slices from tachography, which gives us very high resolution, with much poorer resolution, but fluorescence contrast. And we could really recognize that in this that these features that we observed here were filled with krypton. So they are pores filled with fission gases. And then depending on the burnup of the fuel, depending on the position, we can analyze their pressure, concentration, and more things. Yeah. And in fact, we did it really in 3D. And yeah, you can see here the 3D image. In fact, okay, but I will move forward. And another example was, but here I try to go a bit faster. And another example is tomography of the fuel with a piece of cladding. So you see, this is a part, so again, FIP extracted piece of spent nuclear fuel with a piece of cladding. And here are several tomographic slices based on fluorescence contrast. Yes, so this is slice 1, slice 2, slice 3, just like we have it here on this picture. These red lines indicate the positions where the slices were taken. And here we can nicely see how zirconium is intercalating into the uranium oxide. And in fact, this phase that we see here, which we could then recognize from diffraction contrast, was at the zirconium oxide. So we see the zirconium oxide growing into the fuel. So I will move forward. Then another field of many studies performed at microXAS are biological samples. This is a nice, easy to present example of a comparison based on a fluorescence contrast imaging, comparison of some seeds of plants, comparison between wild and mutated seeds. And we could define here that the distribution of zinc is completely different that in the mutated seeds. The zinc is only on the shell, agglomerated only in the shell, while in the wild case, it's in the whole volume. Another interesting example is the, sorry, went too far. My computer is a bit slow. Okay, excuse me. Let me change. So this is a Daphnia. Daphnia is a waterfly. This is a little organism that is kind of indicator of the quality of water. And this is, but what is important is that this organism is also like a lowest step in the chain, in the natural food chain. And there is a group of our users from Norway. They feed these little animals with all the toxic stuff that they can find, and for instance with uranium. And then here at microXAS we could nicely do the imaging of the whole organism and see where different elements, chemical elements, among others uranium, where do they agglomerate. So if the Daphnia will eat it, will it just go through the whole organism, or will it agglomerate in specific organs and stay there? So that's why this was important. Then another next field that I mentioned that is very important now at microXAS is advanced manufacturing. And we are focused, but not only, on two techniques of so-called 3D printing, so laser powder bed fusion and laser directed energy deposition. So, and we do different types of experiments for this case. So, for instance, here, which was very nice also, actually typical experiment for microXAS beamline is the imaging of chemical distribution of chemical elements at the interface between two different metals. So this is a cross-section of a sample produced with this directed energy directed energy deposition technique. So here we have steel, and on top of it, we have several layers of tungsten. This is a very interesting combination of two materials that actually would have application in also in reactors, but in fusion reactors. So we're using fluorescence and diffraction, microimaging. We can see nicely the distribution of these elements at the interface. We can see the mixing, but also we can see formation from the diffraction contrast of intermetallics. And what is also important, we can see nicely the distribution of FCC phase and BCC phase in the steel part. And interestingly, this was the distribution for one technique, and for the other technique, this laser powder bed fusion, we got completely strange distribution of the BCC and FCC structures. But this is very important for the mechanical properties of such materials. And even though it was expected to have pure BCC. So then what we do is also, and which is also important for maybe applications at micro beamlines, thanks to the fact that we have very small beam, we can actually capture these small areas also operando, where we melt with the laser during this 3D printing. The molten volume is very small, and then the volume which is solidifying is also very small. So to see it in situ, we also have to use the microbeam. And this is an example of the operando diffraction experiment during 3D printing. So this is a machine, miniaturized machine for 3D printing. Here is the box with the KB mirrors, which focus the beam exactly here. And this is the powder bed. And here comes the X-ray beam. So we are sitting somewhere here. Here is the diffraction detector. And we scan with a laser. And during scanning with laser, we can track the diffraction pattern with a very high speed, currently up to 40 kilohertz. And we can see how during solidification we have transformation of different phases in steel. We can see what happens if we put a new material on it. And again, I will not go into details, but just an example. And then another example is this directed energy deposition. So you can see also how we can mount such device in front of the detector. So this is also another laser-based device for 3D printing. And here we also did in situ diffraction. And again, with time, we could see what is happening with the diffraction. So, and now this is a presence. This picture you have seen, but in the presentation of Luc. But what is interesting here, he mentioned it was really impressive how fast they were. And I just wanted to add that this was really crazy, because the guys here, they were actually cutting all the cables. They were not disconnecting anything. They were just, to be faster, everything was just cut and removed super fast. And what will happen now with us, with microXAS? So for us, this upgrade is a big challenge, because actually we are the only beamline that is moving to a different place. So we need to build it completely from scratch. We will get a new undulator. Still, we are not really sure what type of, to be honest, but we hope we will get the new one. And what will change in the new setup? So instead of one pre-focusing beam mirror, which was focusing horizontally and vertically collimating, we will have dynamic focusing in both directions. So as I said, we will also have a different undulator, which and we are aiming for the energy range up to 40 keV, so even higher, significantly higher than up to now, but we stay with this 5, so we still have some overlap with tender beamlines. Then we will have again KB mirrors, but we will get new KB mirrors for the future, and we aim for having 200 nanometers, maybe with some extra lenses with zone plates, maybe 50 nanometers. So, as I said, in the spatial resolution, we aim to get this factor of 5, 200, 100. We'll see what we manage. It's pretty clear that we will have a huge gain in flux. So therefore, we aim for more time-resolved studies, higher energy, and many new configurations. And then very quickly, I want to go through a few examples which Thomas Budvelker shared with me. He's a beamline scientist at Phoenix Beamline, which is similar but operates at a quite tender compared to microXAS energy range. So they also use focus spot-site and scanning imaging. However, they are more focused on spectroscopy, not so much diffraction as we do. So at microXAS, we also do many studies, as I said before, on batteries, but this is also an example that they did at Phoenix. So they prepared a little cell for in operando or in situ studies of batteries. And what was interesting, so they were studying a battery which was believed to that the cycling during charge and discharge is mostly based on a mechanism in redox between iron 2 and 0 redox reaction. But however, this was not well explained just with this reaction. And at this beamline, they noticed that during charge and discharge, also the spectrum of the absorption spectroscopy, EXAF spectrum of phosphorus is changing during charge and discharge. And this is, of course, phosphorus is out of the reach for microXAS, while for them it was possible. Another interesting study at Phoenix was studies of calcifications in breast cancer. So they noticed that only healthy tissue can have extra phase called white locite, a phase containing magnesium, phosphorus, and calcium. And this is again, these are elements that we cannot really study the fluorescence of it or spectroscopy of this. So also using actually diffraction wax, they could image and see the distribution of this white locite into several different tissues, and only the healthy tissue could have this phase, which indicates that maybe this could be also a way how to very early predict the formation of cancer in tissues. Another famous example from this beamline was the studies of the oldest carpet in the world, where they did fluorescence contrast mapping and fluorescence of aluminium. So there is a technique well known, but it was believed to be a few hundred years old. This technique of fermentation of fibers to dye them. But it turned out that, and this fermentation allows for the pigment to go inside the fiber. And the pigment contains aluminium. So the point was that they did this mapping of aluminium in this in the fermented fibers, also fibers extracted from this carpet, and they noticed that they have aluminium also in these fibers inside the fiber while in the natural case, unrefined fibers, the aluminum is only outside. Therefore, they concluded that this technique was known already 2,000 years earlier than people believed. And then that's the last example of the that was also quite famous study at Phoenix of the Stradivari or other very famous, extremely expensive violin instruments. So there was kind of always a mystery why specifically these instruments are so great. And at Phoenix, they could see that actually the pieces, the wood, is soaked, contains some amount of aluminium, which suggests that some special treatment of the wood by Stradivari, before constructing these instruments. So again, this is a spectroscopy on an element that we could hardly access at microXAS. So here I'd like to thank you, and I'm open for questions.
Małgorzata, thank you very much for this very interesting presentation showing enormous research potential of microXAS beamline. Actually, we are running out of time, but maybe if there is one question, you could answer it. Let's have a look.
Okay, if no question, I just wanted to make a remark that actually for me, I didn't realize before that you do experiment in open air.
Yes, we actually do.
Not in some vacuum chamber or something like this, but this system looks so open. I mean, it is just in reality also. It is somehow.
No. Our sample is for ex situ experiments at least is placed indeed in air, and only for cases, if we try to push towards, for instance, aluminium, then we had some systems of blowing with helium on the sample. Still, it was open. So in this energy range, it's possible. While if you go lower, then it would be problematic. Yes.
This changes of this last mirrors, focusing mirrors. How you do it? Is just some switching stuff, or you do it each time by hand?
So you mean the KB mirrors for focusing of the beam?
To change focus.
Yeah, so that's actually quite a drawback at our, well, I wouldn't say drawback, but yeah, that's a bit a thing to do at our beamline, that indeed every experiment requires refocusing. Yeah, every time we change energy, we need to focus again. And we do it essentially manually. We have actuators on the mirrors, on the benders, and we just manually scan over the applied force, so to say, of and see what gives the best focus possible. And it's kind of art, So it's also kind of competition at the beamline, who can focus better. But we need to do it every time, for every experiment, indeed.
Okay, I can see there is one more question from Galyna Dovbeshko.
So, Małgorzata, thank you very much for a very interesting report. And my question is about what low limit of concentration of metals can you detect in biological samples?
So, of course, that depends on the sample. So it's essentially it's ppms, single ppms. We can
ppm, yes.
Yes, but then it also depends on the sample. What will be because we are talking about fluorescence, and then what will be the self-absorption of the fluorescence in the sample? How big is the sample? Does it manage the emitted fluorescence doesn't manage to get out from the sample. So this is always a question. But if the geometry is perfect, no issues with self-absorption, then it's single ppms. Yes.
Okay, thank you. And really, is it possible to apply to you with this problem?
Of course, but in 2026, because now we have this big upgrade, which will last until late of 25. However, our beamline is in the last phase of upgrade, and our beamline will be available for a user program maybe in the mid of 26. But if you have any questions, feel free to contact me. We can also, I could also suggest other beamlines at different synchrotrons. Yeah, if there is a hurry.
Okay, thank you very much. And I suggest if you have some more questions, please write them in a group chat. And Małgorzata, I will ask you to answer them if some appear. Okay, and we have to move on to the next speaker. So Małgorzata, thank you very much once again for the great presentation. And our next speaker is Marine Cotte. Marine is beamline responsible of ID21 beamline at the ESRF in France. And she's going to talk about nano-spectroscopy in the tender X-ray domain. So the stage is yours, Marine, please.
Thank you, Eva. I hope you can hear me well.
Yes, we can hear you. We can see your presentation and the pointer as well.
Super. So I also hope that my computer will be efficient enough. So first of all, many thanks to the organizers and Jakub in particular for the kind invitation. I think it's not so often that we have this kind of discussion about nano-spectroscopy or microspectroscopy in the tender X-ray domain, and I'm very, very looking forward the presentation and discussion today. So ID21 was built in the 90s already with the idea to offer spectroscopy in the tender X-ray domain. And over the last 5 years, we benefited from an important refurbishment. So this is something I will present during my talk. So first, if I can switch to the next slide. Okay, oops, sorry. So first of all, let's a short presentation of the beamline team who takes care about the maintenance, development, and the operation of the beamline. And something which is, I think, interesting and a bit particular for ID21 is the scientific communities. So here you have a graph showing the statistics over the ESRF, where with the very important scientific domains such as hard condensed matter science, applied matter science, chemistry, structural biology. And if we make a zoom only on ID21, you see that we have users who are coming from very, very different fields and not the main ones. So in particular, earth science, life science, medicine, environment, and cultural heritage as well, which is an important activity at the beamline. So I think this is a peculiarity of the microspectroscopy beamline in the tender X-ray range, and which should be considered probably for the future SOLARIS beamline. So a few, let's say, trends or keywords for these 5 main scientific topics. So in cultural heritage, the 2 main questions are, can we get information, insight about masters' secrets? And on the other hand, how and why artworks degrade in some cases. We also, environmental science is also a very, very important field where usually we are interested in the fate of manufactured materials in the environment with sometimes positive and sometimes negative impacts. And other examples are the accumulation of metals in plants. Health is also a subject where we are interested in the interaction of manufactured and biological systems. For example, the case of tattoos, drugs, implants, and so on. And we also have research or experiments dedicated to understand biological phenomena. For example, chemical modifications induced by the neurodegenerative diseases. Earth and planetary science are important as well, where users will use X-ray fluorescence and spectroscopy to get chemical signatures, and such that they can get information or deduce information about geological processes, or also study paleoclimate. And maybe 5 or 10% of our activities are dedicated to manufacture materials. For example, as shown here, solid oxide fuel cells, and where users are interested in what happens at surfaces or interfaces, and with notably diffusion of elements or chemical reactions at boundaries. So to fix a bit the idea, so globally, the users, they want usually to have both identification and location of chemical markers in complex materials. So to show you in practice what it means in experiments at ID21, I have chosen two illustrative case studies in two domains which are important at ID21. On the left, cultural heritage, and on the right, environmental science. In these two cases, users were interested in cadmium. On the left, this was about the degradation of cadmium yellow pigments in the screen. And on the right, the fact that regulation evolves and that in some countries, the natural level of cadmium is too high and creates a risk of problems with respect to contamination of cadmium in cacao. So these are the key questions. How does cadmium yellow degrade in the screen, and why? What is the cadmium path from the soil to cacao beans? So this is how experiments will run usually at ID21. Users, they come with fragments. So we did not bring the full screen, but only a fragment of it. And on the other hand, we add cross sections or thin sections of cacao seeds. And then we start with 2D microfluorescence map, such that we can identify and locate elements. So in this case, sulfur and cadmium. And on the other hand, we see where is cadmium, how deep it penetrates into the seeds. Just to let you know that we don't offer 3D mapping. And the second step is usually to tackle the chemistry. So this can be done using xanes typically. So here you have examples of xanes at the sulfur K edge, where we can see that depending where you are on the paint fragments, the signal is not the same. And in addition to the original cadmium sulfide, which is a pigment, we observe also agglomerates of sulfates. And in some cases, we can go further and try to map these different species. So in the case of the Munch cadmium yellow, what we did is that we acquired the same map at two energies, which are shown in red and green. So this is multispectral mapping, but in the future, this is something we would like really to stabilize and make more efficient by increasing the speed, such that we can acquire these kind of multi-energy maps at tens or hundreds of energies. So in summary, the link between these two examples is the fact that we have a lot of non-expert users who aim at identifying and localizing various species from major to trace elements. Also, something which is important is that the samples usually contain both low-Z elements like phosphorus, sulfur, and metals, usually in biological matrices, but often complex and heterogeneous, and so they need submicrometric resolution, but still large field of view in the range of submillimetric range. So here you have the elements which can be detected. So these are the ones which are in color, and the ones which are in bold as those for which we can do absorption spectroscopy. And then here I summarized a couple of applications to cultural heritage. So with the case of cadmium yellow, globally, the common motivation or objective is to understand why some pigments or some materials under specific conditions like light, temperature, and humidity, they degrade. And we use fluorescence to identify elements and xanes to get information about these chemical reactions. So other examples are degradation of chrome yellows, of smalt, of emerald green, or also not talking about degradation, but understanding the composition of some components. We analyzed the support of Leonardo's codex. We also analyzed inks in papyrus and different chemical products used for the consolidation of limestones. So this shows you how diverse can be the cases. And if I switch to health and environmental science, you will see as well that we tackle many scientific problems. So for example, here you have many analyses where users were interested in the location and speciation of 3D transition metals in various biological systems, like in agriculture, in soils, also asbestos in lugs, and so on. But beyond 3D transition metals, we can also study many heavier metals, such as silver, cadmium, indium, tin, and so on, thanks to their L edges. And I think this is something which is very interesting in the tender X-ray domain. So this is a sketch just to, I would say this sketch represents about half of the experiments that we do at ID21. We usually have a biological system which is interacting with the exogenous, usually manufactured materials, and we want to understand how the biological system reacts and how also possibly the exogenous material is concentrated, is modified from a chemical point of view, and so on. And this both in the case of intentional use or in the case of incidental exposure. This is a sketch of the beamline as it was in 2016, and probably a bit similar to what Jakub saw when he was a postdoc with us. So at that time, in 2016, we had 4 installations. The main one was scanning X-ray microscopy in the tender X-ray range, at that time from 2 to 9 kV. We were also offering XANES in full field mode, a station for microdiffraction, and the infrared microscope. So at that time, we were invited to think about the future of the beamline and the refurbishment and what was the strategy for investment in terms of budget and resources. And we decided to concentrate on spectromicroscopy with several objectives. So to extend the energy range, to make the switch from cryo to room temperature easier, to get a smaller beam, to better collect its reflorescence, and to keep microXAS absorption spectroscopy as a key technique, but extended to 2D whenever possible. So the refurbishment was split into 3 parts. The first part was about the primary optics and optics hutch. The second part was the installation of the first prototype of new double crystal monochromator. And the third part, which is still ongoing and finishing now, is the installation of a new nanoscope. So this is a sketch of all the things which happened since 2018. So the first part was ended in 2018. We got the DCM just before the ESRF was closed, so it was a bit frustrating because we had to wait for the beam to come back to continue the commissioning of the monochromator. We had the first EBS users in 2020, and then we had the second shutdown for different installation in the experiment hutch. We took the beam back in 2022, and the nanoscope itself was installed in 2023, and we spent last year installing different parts in it, and the first beam was taken in the nanoscope in December. So some major technical achievements which were achieved in 2018-2022. So as I was mentioning, we are the first beamline benefiting from this new generation of double crystal monochromator for spectroscopy. The purpose being to have a beam as stable as possible, both in static and in dynamic conditions. There is a huge upgrade or migration of the control software from spec to BLIS. So ID21 was among the first. Something which is very important for us is a graphical user interface. If you have in mind our users coming from cultural heritage, from environmental science, they need to have a microscope which is, I would say, as easy to use as an optical microscope or electron microscope. And this is possible thanks to daiquiri or graphical user interface. And also something I think which is highly appreciated by our users is all the work which has been done or which is still being done for data policy, notably electrical logbook, the data structure, metadata structure, to make things as automated as possible and as user-friendly as possible. So even if the refurbishment is not completed now, we can already see impacts or improvement compared to before EBS. So notably, the fact that we have now the new EBS source, the flux is much higher. And the example I showed you about cadmium in cacao is only possible because we have an increased flux offered by EBS, and also because we are pushing further our X-ray fluorescence detector. On the other hand, when we are working on nanoparticles, XANES on nanoparticles, Without the present monochromator, it was very difficult to get good Xen spectra on nanoparticles, because even if the beam is small, it's like 0.3 microns vertical, 0.8 horizontal. If the beam is moving over 1 micron and you are trying to scan a nanoparticle of 100 nanometers, you will get this kind of structures which are just artifacts. So we had a solution which was a bit turning around in the past by acquisition of maps, but now that we have the new monochromator, the beam is stable enough so that we can stay centered on nanoparticles and that we can get decent Xen spectra also on nanomaterials. So briefly, what will offer the new X-ray nanoscope? So we have kept the historical scanning X-ray microscope, in particular for the study of larger samples which do not require an ultimate resolution. Both nanoscopes operate in the same tender X-ray range from 2 to 11 kV. The two main techniques are X-ray fluorescence and X-ray absorption spectroscopy. But as I was saying, by increasing the speed, we hope to make multi-energy maps as accessible as possible. We always work under vacuum, and we can work either in cryo condition or at room temperature. Now, what are the differences between these two instruments? So as I was saying, we keep the old microscope for unfocused beam or medium size. And with the new nanoscope, we hope ultimately to reach a beam of 100 nanometer. But now in December, we reach a beam of 200 nanometers, which is already very good. In the old microscope, we have only 1 kb, which is coated with nickel. This is very good in the range 2 to 8 kV, but above the nickel K edge, the flux is not that good, and also we cannot do nickel Xens. So this was the reason why we have now in the new nanoscope 2 kbs, one coated with nickel and the second with platinum, such that we can give a very high flux over the entire energy range. And also something which will be very, very important is the fact that in the past, we had only a single element X-ray fluorescence detector, and with the new nanoscope, we will have 2 5-elements X-ray fluorescence detector, meaning that the detection of the fluorescence will be much more efficient. So what are the directions for future development? So first, the priority is to complete the commissioning of the new nanoscope, and this is really ongoing. And then as soon as we make it available to users, for sure, we will have to work on developing different sample holders to get them easy to use and to switch from one station to another or one beamline to another. An action we started about 5 years ago, and which is also super important, is to consider that provide users with data is good, but if they are not able to process this data or analyze this data, all our work is useless. So there is a huge action at the ESRF towards data analysis as a service, and notably the development of workflows. And so this is something that we want really to push forward in the future. And also something which is important that our management is pushing us as much as possible is to increase the transversality among beamlines and not to stay focused at the level of beamlines. And with this, I will thank you for your attention. I'm very happy to answer your question, and I thank all our users and colleagues involved in this research.
Aline, thank you very much for this great presentation and information about the refurbished ID21 beamline. And maybe we have time for one question because we are late, a little bit late. And is there any question? I can see already. Alexander Kordyuk, yes, please.
Okay, I just wanted from point of view physics condensed matter and about cryostage. Cryostage, yes. What is the reason for you to use cryostage? What's the main motivation, and which temperature it's allowed?
Yeah, so it's a liquid nitrogen cryostage. Typically, this is for biological samples. That if you want to get first, you want to preserve your sample, but also that your Xen spectra are not too much modified under the X-ray beam. It's much better to work in cryo conditions.
Okay, have you seen the examples of using your equipment, your beamline for let's say investigation of the samples under current, for example, electrical current. For example, it would be interesting. I could imagine to investigate memristors, for example, about the distribution of the diffusion of some elements. Is it so the
this
case?
Is not possible at ID21. We have very limited in situ, let's say, conditions. Basically, only cryo. We do not offer fluid capabilities, or we did in the past, but very occasionally. The design is not relevant or is not adapted for this kind of in situ experiments. But this is probably something which should be taken into account for the design of this new Solaris beamline, because these are the things you should consider from the very beginning to make sure that everything around the sample is optimized for this kind of in operando or in situ experiments.
Okay, thank you.
Okay, there is one more question from Małgorzata Makowska. Yes, please.
Thank you. So I just wanted to ask about your monochromator. So I didn't get it. Is it horizontal or vertical?
Vertical.
Okay. And then this great stability that you have within 1 micron, do you have some position feedback to the monochromator, or is it really just what you get?
The way we use it is based on interferometers. So we build basically calibrations. So we start a calibration of the monochromator by observing the beam position and by building tables such that you try to keep the beam as stable as possible. And then you use this table to somehow to correct the position and distance of the second crystal with respect to the first one. This is not, but then this correction is not, you don't measure the beam position in real time, but you measure the crystal position in real time thanks to interferometers. So you make the hypothesis that the calibration you have built and the table you have built is stable over the time. But ultimately, there could be an online feedback based on beam position. But at ID21, we cannot measure simultaneously the beam position and the sample signal. So we make the hypothesis that the beam drift is stable, which is in the main drift is indeed repeatable.
Okay, thank you.
There is one more question from Luc Patthey. Yes, please.
Hello, thank you. Thank you for Marie for this very interesting, impressive talk. I have questions for the new beamlines. Did you use completely new insertion device, or you still have this? I think you had this Wiggler 80 and ondulator 40 and 42, or what is the situation? Can you?
But after the EBS, many beamlines kept their previous ondulators. In some cases, I think the straight section was too short, so some users had by default to change their ondulators or insertion device because it was no longer fitting into the geometry of the source. At ID21, we did not make any change. But I know that there are many beamlines, for example, which are going towards in vacuum ondulators or cryo ondulators.
Yeah.
So, but there is no single answer to your question. But for what we are concerned, we kept our ondulators, which are pretty good.
Okay.
Yeah.
Okay, good. This is what I wanted to know. Thank you.
Okay.
Okay, Marin, thank you very much for your presentation. And now we move on to the next presentation, which will be given by Delphine Vantelon, who is beamline manager of LUCIA beamline at Soleil synchrotron. And she will be talking about chemical imaging and speciation in the tender X-ray domain at this beamline. So please, the floor is yours. Could you please switch on your microphone? We cannot hear you. We can see your presentation, but we cannot hear you.
Yeah, can you hear me?
Yes, now it works. Okay, thank you very much.
Yeah, sorry, I made some mistakes with the screen sharing, and So now you should be able to see my my laser pointer. Yeah, so thank you very much for inviting me to present the LUCIA capabilities and the specificities to this workshop. And maybe it will have a little sisters in Solaris, so I understood. Yeah, so LUCIA, so yeah, I will present you these capabilities, but also LUCIA is a team, and which is composed by Damien Roy, who is our assistant engineer. We are 4 beamline scientists, Camille Rivard from the INRAE, Nicolas Tresserra, Bénédicte Lassalle, and myself. And currently the staff is complemented with Pierre Lagarde in Emeritus and Anna Pradas as a postdoctoral fellow. So, LUCIA is the thunder X-ray beamline of Soleil dedicated to element mapping and speciation by X-ray fluorescence and XAS coupling. So it means that we are working in the 0.6 to 8.5 keV energy range, and the beam can be as large as 2.5 millimeter or focus down 2.5 micrometer. Then in this case, we can map in an heterogeneous sample, we can map the elements that are reported in this Mendeleev table. You can see an example of map here, and on specific location of the map, we can collect the XAS, either XNS or XAFs, to obtain the speciation of the element, its oxidation state, and electronic and atomic local environment. And this can be done on samples, as you will see, that are super heterogeneous, so some liquid, solid, or ordered or amorphous samples. And the detection limit is rather low because of the fact that we are on an undulator, the source is an undulator. And also to cover the whole energy range, the beamline has a monochromator that is composed of a DCM with several crystals and a multi-layer grating monochromator to cover the low energy range. And it is working with this focusing mirror and an exit slit after the monochromator. And then the beam can be focused, translating KB mirrors into the beam as the last mirrors, optics of the beamline. And so you can translate them into the beam or remove them to the beam to have the focus of the macro beam size. And then the beam enter into the experimental chamber. You have a picture here of the permanent experimental chamber and an image of the inside of the chamber here. We have 3 methods of detection that can be used together. A fluorescence detection with a 60 millimeter square SDD currently. We can measure also the current of the sample, and then we get the total electron yield. And we can also measure transmission, if possible, using a silicon diode installed on after the sample. We also have 2 movable vessels that can be installed behind the permanent one. One that is under UHV, sorry, for surface science, and one that we are currently still building, but still it is already usable, but not really complete, which is dedicated to operando in situ experiment and liquid cells. So the samples, as I said, they can be numerous, liquid, mud, solid. Can use powder and deposit them on carbon tape or pressed into pellet. We can work on massive samples or thin sections that can be cryogenic, freeze-dried, or embedded into resin. We can work on cells. And I will show you on complete little specimens. They can be able to enter into the little space of the vessel, as yes, I have to mention that the constraint is that we are working under vacuum because we are working in the thunder X-ray domain. So then the samples are installed on copper plates. with variable design adapted to the different samples we can measure. And also, we have developed some sample environments compatible with the vacuum to work on the samples under constraint, such as the temperature constraint or pressure. For temperature, we have a furnace, but we also have a helium cryostat on which we can set the energy, and then you can study phase transitions with a low temperature. And we are also currently working on the homemade reaction cells for microfluidic or electrochemistry operando experiments. Then, as all XAS beamline and as ID21 and also microXAS, LUCIA is welcoming users from many scientific communities. The main one on LUCIA are from geoscience, environment, and material science, with overlaps, of course. Also, we have an increasing community coming from biogeochemistry and health science and chemistry demanding operando measurements. And we have a continuous little number of teams working on surface science, and we receive few proposals from cultural heritage, certainly because they are all going on ID21, but we have some sometimes. And then I will give you, in fact, a quick overview of all the experiments, all the experiments we can perform on such a tender X-ray beamline. For geoscience, environmental, and biogeochemistry, I will use metals to make a sort of common thread. Then on the metals, when they occur as naturally in the environment, but then when they are waste from human, and then after the waste and transfer, what happens when they are ingested by living organisms. Then I will switch to the study of materials with materials for catalysis, just the study of the structure and the structuring during operando functioning. And also what we can do under constraint with pressure and temperature. And I will finish with surface science. Yeah, so in this case, on geoscience, our users wanted to study the evolution of the scandium speciation during the alteration process in a profile depth from the parent rock to the surface. So they collected samples at different depths of the profile, and they measured the scandium K edge zones, and they used them as a fingerprint to follow the scandium modification, the modification of the scandium speciation and its evolution with alteration. And they also use calculation of xanes. For example, in this case of scandium linked to goethite, to really decipher if scandium is adsorbed or introduced into the goethite structure, that would have some consequences of the scandium availability. Then when the scandium heavy metal is extracted, it is used in metals and, for example, in plastics. And here is an example of what is inside a plastic altered, weathered, collected on a beach. Here you have an image, an ESRF image of the section. You see the cracks at the surface of the plastics and all the metals that, part of all the metals that contain the plastic, some of them being toxic. And so clearly with the alteration, you see here at the hotspot of chromium, with the alteration, you have a release of these toxic metals into the environment and performing xanes and EXAFs at the chromium edge in different locations of the map. Users could observe that chromium occurs in this sample as a chromium-3 linked to the polymer of the plastic, but also as a cobalt chromite nanoparticle. And also as chrom6, which is the toxic form of chromium, as associated with lead in crocoite, or with potassium as a chromate potassium. So then the plastic weathering, as said, release the toxic metals in the environment. And then when it is released, it is transferred in the hydrosphere and can be trapped by colloids. And here is a study of a structure of colloids and how it evolves with the variable physicochemical parameters where it is sitting. Here the study is the evolution of calcium concentration. So when calcium when there is calcium interact with the organic matter, forming dimers, bridging the organic matter. And this was demonstrated by the EXAFs at the calcium KH performed on the different colloids. And then when calcium bridge the organic matter, you have an increase of the size of the overall colloid that settle. But also you have a liberation of the sites at the surface of the ferrohydride that can grow up a little bit, but also trap more metals such as arsenic that has affinity with this ferrohydride. So in this case, the colloid traps more arsenic and immobilize it at in the sediment of the water system. Then metals can be ingested. Here is a study of the ingestion of colloidal silver suspension by mouses and what happens in the colon of these mouses, as the users have demonstrated that the colon is damaged by this ingestion. And here you have an image, ESRF image of the section of the colon. And you see with the map of silver and sulfur that they are colocalized, and with the xenes at the silver age, that in fact the silver changes its speciation to form complexes with the chiral groups of protein or peptides. Here is an additional study on the effect of ingestion of rare earths and the toxicity of Daphnia, because here, as you can see, we could study the whole specimen, it is small enough, and with sulfur we follow the organisms of this Daphnia. And here you have the location of the lanthanum in the intestinal tract. And here you have the distribution of the gadolinium, which is now in the tissues. And the users observed that the gadolinium was more toxic than the lanthanum. And here we could observe that it is localized in the organisms of the species, in the tissues. Yeah, now I switch to material science. And here is the study of the ex situ study of what happened during the synthesis of the cerium oxide that can be used in catalysis, either as support or as an active phase. And so these users could see that during certain processes of synthesis, they could reveal an unexpected phase of cerium hydroxide with the cerium LH xenes. With this phase is this one in green, and then they could determine the structure formed, the intermediate structure form that can have an impact on the final phase, its stability and its efficiency according to the synthesis protocol people can use. Then I show you two examples of in situ modification of materials under constraint. Here is under high pressure in an anvil, in a diamond anvil cell that is dedicated to LUCIA, as it allows to use thin diamond to allow the transmission. And so here we can reach 50 gigapascal. And here you can see that with the EXAFs, they could see that above 45 gigapascal, they observed the symmetrization of the iron octahedra. And with the XANES and the FDMNS calculation, they could observe a high to low spin crossover of the iron 3+, also above 45 gigapascal. Now I switch to the modification under temperature, here of nanotubes of imogolite. And so we use a furnace up to 800 degrees Celsius. And the users followed the transformation of the nanotube of the imogolite to layers which with a mullet-like structure. And during the heating in situ, they could observe the transformation of aluminium with the XANES from octahedral organization to pentahedral and then tetrahedral. I have to mention that this was measured with macro beam. So macro beam has also an interest, not only micro or nano. And so now here a report of one of our first operando observation of reduction of CO2 with the catalyst that is iron tetraphenyl porphyrin, studied at the iron cage, so with a homemade electrochemical cell. And so following the iron speciation with the XANES, they could determine the modification of this TPPC, I think they call that, during the catalysis. And also they could determine the structure that is in orange here, that the reduced species, that is the active form of the catalyst during the catalysis. And then I finish with surface science. These users could follow the arrangement of silver clusters on different surfaces, magnesium and magnesium oxide and aluminium oxide, and in fact depositing different layers and amount of silver on the surface. They could observe that below 3 nanometers of particle size, then the silver is forming monolayers. They followed it with the examples of silver. They form monolayers, and which distances, furthermore, IgIg distances in the cluster is determined by the lattice of the support. Here magnesium oxide and here aluminium oxide. With the magnesium oxide, there is for very low deposit, there is a weak bonding that allow the constraint to be removed. And then above 3 nanometers, the silver coverage is high enough to allow the formation of 3D clusters in which the AgAg distances are the one of bulk silver. Voilà. I have finished the quick overview of the examples of science we can perform on the line. And then to finish, I will also remind you that in the tandem X-ray domain, we can work on numerous types of samples with many scientific applications, and we can develop many samples environments, just taking into account that we are working under vacuum. And in the case of LUCIA, according to the evolution of the demand of the beamline, the users are demanding for more in situ operando experiments. So we are currently developing the fly scan also for the EXAFs on the whole energy range, and we expect to have it to provide it to users in 2025. Also, they are asking for better spatial resolution, and we are working on building a new experimental station with a beam size at around 500 nanometers, also ready in 2025, we expect. And then with Soleil 2 in 2030, I think, we will get higher flux. Furthermore, we will move, so LUCIA will move and change its undulator to a more to a one that will give more energy, more flux, sorry. And I thank you for your attention.
Thank you very much for this very impressive presentation and showing us the research capabilities of LUCIA beamline. Do we have any questions? Luc Patthey, please.
Hello, Delphine.
Hello.
Thank you for your presentations. Nice to see the evolution from LUCIA. I have a question. I would like to understand, actually, from your point of view, actually, what are the impact or the developments on samples which are related to magnetismus? I mean, your beamlines can go fairly down and approach really important edge, which are relevant for magnetismus. But do these things still active, or how is it regarding to the rest of the landscape of the research? Can you comment?
Yeah, there is a beamline at Soleil dedicated to magnetism study.
No, but for at LUCIA, you have also this capability, right?
Alors, well, we have due to the undulator, we have the possibility normally to perform circular or linear variable polarization. When they build up the undulator, at one point we had to select either we want to a linear polarization or a circular polarization, because if they improve one, it was at the expense of the other one. So because there is a beamline dedicated to XMCD at Soleil, we didn't take this option. And I have to mention that we have the option for variable linear polarization that almost nobody asked for. That's why in far future, but with Soleil 2, the machine staff proposes to have another undulator without this possibility, because in fact it was not used. So we don't have this this magnetism community at LUCIA, in fact, at the end.
Okay, thank you.
I do not see any questions. There is still the possibility to write in a chat. Even later on, you can just write in a chat your question. Yeah, we do not have more questions. So Delphine, thank you very much for your wonderful presentation. And now we move to the last talk in this session. And it's my pleasure to welcome Professor Alexander Kordyuk, who is a director and professor of the Department of Applied Physics and Nanomaterials at Kyiv Academic University. And he's also actively working in Light for Ukraine project to appoint Ukrainian Synchrotron-association. And today we will get some information on Ukrainian Synchrotron-association. So Sasha, the stage is yours, please.
Okay, thank you. Thank you. Could you see my screen? Yeah.
Yes, I can see. We can hear you.
Okay. Thank you very much. I think I will be shorter than 20 minutes. I will not take much of your time, especially now. And one moment, please. Okay. So I would start with the slide which I presented in Strasbourg at the LIPS meeting, and just wanted to say that actually thanks to LIPS and Solaris people, we started to establish our Ukrainian synchrotron society. We have many people in Ukraine interested in synchrotron studies and experience in synchrotron experiments. I think, I think that requirements and potential is much more, and it is interesting thing about. It is important thing for us. And the first Light for Ukraine workshop has shown that it is really great interest from the people. Now we are more specialized. And I just will say a few words about this. So what we did, we had some survey also. We have survey from Solaris and from our side to define the area of interest and area of experience. And you see here, just summarizing about 60 responses, that we have more experienced people answered, but still, and we have people who wants to start these experiments, synchrotron experiments. You see here that actually the experienced people are more than 50%, since these are just experience, and this color sectors, they are for people who give exactly names their experience at different beamlines. It's interesting about research area in a sense that, as it was expected, we have more physics interested physicists and material scientists, but this is also because I'm physicist, and we started this from distribute information through physics people, starting from them. And but we have also interest from chemistry people and biophysics, biology and medicine, and I'm sure that we have a lot of people interested in air sciences and in art research related, like was presented here. Therefore, we have a great potential for growing this society. Looking for experience, this is a small just rating of the synchrotrons, just experience where Ukrainian researchers used, and this is the leader of DESI. I think it's somehow mostly Petra, I think. Also Electra synchrotron, ESRF, and BESI. So you see these numbers. This is of course not 100% objective, but we have such responses anyway, and some experience also on lasers. If you experience on lasers, and here is HN100, it is our people in Kharkiv, in Physical Technical Institute in Kharkov. They experienced in actually producing linear accelerators and using them for different, also for medicine actually. It is about interest, what people express their interest in, what they're interested in participation of this research, and most of the people say that they're interested in building Eastern European synchrotron in Ukraine, but also people are very interested in research at European synchrotrons, but also in building joint beamlines like at Solaris, and in organization of the society and formation of the society itself. And it was shown already. It is taken. This picture is taken from the Luc and Anna's report, but Jakub have shown it that expressed people expressed interest in the survey launched by Solaris, that it is most of the people are really interested in this nano-micro X-ray spectroscopy, which Luc has presented already, so I skip it just to emphasize again for our people that we expect here the operation from 2 kilo EV to 7 or less, I think, but something like this. And we had it, so we had this information from Luc already. Thank you. I think potential of our now it is about 50 people registered, pre-registered, let's say, in our Ukrainian synchrotron society, and I would say that close potential for the next year it is 60-100 members. I expect maybe more. And here is a link to join. Here, in principle, it is Telegram group, and before it was the link about this survey was also. It's easy to join now. And thanks to Professor Cormac, that Ukraine is now already elected chosen became 32nd European member of Europe of this European Synchrotron User Organization. We started from discussion of our statute, and also we have changed the name, which it was initial name, but now it is called Ukrainian Synchrotron Community. And we have performed some work in statute, and we expected to register soon, to register officially in Ukraine. Of course, we discussed specification of the specialization of this future beamline at SOLARIS, and the last thing it was to register in the nephew project to raise the expression of interest. And about the nephew project, actually there is no place to advertise it, but actually it is the link about this our expression of the interest. There we have shown briefly the potential. Actually, there were very many institutions in Ukraine. They're interested, as I said, now mainly in physics and material science, but also substantial part it is chemistry direction and biological direction. They are also very strong, and I think they are not less strong as physicists. Therefore, we will see. We will expect the growth of interest from these people. We also, this is at least. We have declared support from Ministry of Education and Science, of course, from National Academy of Sciences. They support this progress, and we hope in future to involve and National Research Foundation of Ukraine and other Ukrainian societies. What is the most interesting for people, how it was for Ukrainian people, and it is, of course, support of the access of the synchrotron access. Actually, I wanted to say, wanted to ask all three lecturers about possibility of remote access, which is also important for us. And this question is also interested about remote experiment and, of course, some kind of training courses, training efforts for our people, because we have some experienced people who know how to apply for beam time and how to write this projects, but also we have a lot of people who do not know, and I think we should teach them how to do this, and this is one of the important ideas of this society. That is it what I wanted to tell you about society. I want again to express very to say that I'm very grateful to all the people who involved in motivation of to motivate us, to help us, and this is Anna Vach and Jakub and Marek and many people at Solaris and Luc and Leonid and people in Lips and Cormac, and of course I'm grateful to Armed Forces of Ukraine. They could give us possibility to do it now, and I'm grateful for all of you. Thank you.
Sasha, thank you very much, and it's really nice to hear that the Ukrainian synchrotron community is growing. There is one notice in a chat from Lawrence Norris from African Light Source. Let me just read it. So let me indicate on behalf of the African Light Source Foundation that we are interested in collaborating with the Ukrainian synchrotron community in any way we can. Yeah, so great opportunity to work together. Do we have any questions? I do not see any questions. So yeah, let me just conclude this session by thanking all the speakers for providing us with a great set of interesting presentations. And I would like to thank you, all of you, for joining the session. And now we will have a break, and the next session will start 1:30. So see you later, and enjoy your lunch.
Thank you all. See you.
Thank you, Sasha, once again.
Okay. So good afternoon. I will chair the session, and I'm Alexander Kordyuk, as you may know already, if you've been in previous session. We plan to devote this session to the speakers from Ukraine to consider these talks, this presentation as examples. Who are interested with their research are interested in the future beamline at Solaris. The first speaker, Volodymyr Karbivskyy. He is from the Institute of Metal Physics, and he is the head of department and of this Center of User Facility. I think he will tell a bit about this. Please, Volodya.
Thank you, Sasha. Good afternoon. Title of my presentation, Research of Novel Materials to Address Energy Production and Storage Challenges with the Use Synchrotron-based Nano-X-ray Spectroscopy Techniques. We are talking about materials for green energy. In 2023, the volume of investments in the solar energy sector exceeded oil production for the first time. This is according to the Business Insider materials. This slide shows the change in solar cell efficiency over the past half century. The efficiency of solar cell based on perovskite orange curve has changed from 12 to 26%. At CTEC Japan 2023, Panasonic presented solar panels based on perovskite with sufficient transparency to be used as windows. The efficiency of such panels is 17.9%. Sorry. Also, in 2023, China launched the world's first silicon-free power plant with a capacity of 1 million watts. Here is the structure of the solar cell based on perovskite, which consists of metals, hole instruction, perovskite, electron instruction, ITO, and glasses. We plan to use perovskite of the following composition. Today, it's known that the highest efficiency of solar cell is observed for mixed dimensional perovskites. So it's necessary to study the extraction by synchrotron-based nano-X-ray spectroscopy techniques. This slide shows the main advantages of solar cell based on perovskite. However, there is also a significant drawback due to the presence of toxic elements in the structure, which when such a compound comes into contact with water and oxygen, as well as when it's periodically heated, can be chemically unstable and degrade rapidly with the destruction of the structure. It's very important to solve the problem of lead. It's well known that in the 20th century it cost 100 million deaths and took away 825 million IQ points from humanity. For many countries, there is a correlation between two courses, the crime course and the wood lead course. The correlation is observed with an interval of 20 years. To build a solar cell, we use organic and inorganic perovskite of the following composition. And in 2013, Science magazine names such perovskites as the most promising materials. Halide perovskites are considered the most promising due to a number of parameters. Halide perovskites are soft ionic electronic materials with weak bond and high ionic motion. They must be engineered to make them stable. This slide shows how the presence of an encapsulating layers can solve the problem of temperature, moisture, ultraviolet radiation. And hydroxyapatite is the most suitable materials for such layers, as it's a multifunctional materials. Because hydroxyapatite is excellent sorbent and have good photovoltaic transparency. And so the goal of the project to establish the mechanism of stability and efficiency of the components of perovskite solar cell with protective component based on calcium apatite, and to develop the infrastructure for this research, in particular the Ukrainian beamline at the SOLARIS synchrotron. Apatite a very broad class of compound. Our task will be to find the most suitable apatite. The atomic structure is shown on this slide. Visualization structure. And since the result of monotone deposition apatite is formed in the form of clusters, the study of its structure will be most informative using synchrotron method, in particular EXAS and EXANES method. The EXAS technique is presented on this slide. After absorbing quantum, the atom became a source of the divergent electron wave. After the wave is reflected from neighboring atoms and interferes with the original wave, oscillation in the absorption coefficient appear. And the application of the Fourier transform gives a function of the radial distribution on atoms. Only use of synchrotron can provide a solution to the structural problem for disordered systems. For example, a binary system requires 3 equations, and only a synchrotron can provide different absorption edges of the elements with coefficient resolution. And on this slide, you can see the function of the radial distribution of atom in the bone mineral and the nano-dispersed calcium apatite with a specific surface area of 600 square meter per gram. The first calcium coordination sphere for synthetic apatites and bone mineral is almost identical. However, the highest coordination spheres have lower intensity. In the bone mineral indicated a highest level of disorder in the bone apatite. The EXAS method allows us to identify the most characteristic fragment of the structure of amorphous calcium apatite, which can be seen on these slides. The use of isomorphical substitution in both the cationic and anionic sublattice apatites can control the width of the gap, band gap. So the project will provide pathway for the rational design of more efficient and environmentally friendly materials, and at the same time continues the development of the Ukrainian synchrotron infrastructure for X-ray imaging and spectroscopy application, which will be installed at the SOLARIS synchrotron and used in the future by the Ukrainian synchrotron community. Thank you very much for your attention.
Thank you, Volodymyr. Please, questions? While you're thinking about the questions, I wanted to ask just about peculiarity of electronic structure. You said that you are looking for appropriate apatite, so it should be with largest gap or smallest gap. What is which one is good for this cells?
Many transparency in the region of the working solar cell. Maybe this compound about 4 electron volt.
Mm-hmm. About 4 electron volts, it's optimal, yeah?
Yes, it's optimal.
Mm-hmm. But this is results of it's experiment. I see. It's experiment.
This is experiment. Yes.
And in experiment, it is larger than in calculation.
Sorry.
Okay, clear. So, thank you. More questions? Okay, if not the case, thank the speaker, and we switch to even more chemical, I think, problem. So Yaroslav Odarchenko from United Kingdom now. Yes, do we have Yaroslav here?
Yes, good afternoon to everyone. Yeah.
Please, you can share the screen.
So just a second.
Hello, good afternoon to everyone. Yeah, just once again, I just would like to check whether you can see my slide. Oh, sorry.
Yeah, we can see, but if you maximize, okay, perfect.
Wait a second, I will just make it more louder. Like this, yeah?
No, it was okay. You mean the volume of the sound? Sound is good. Okay.
Okay. So basically, yeah, I would like to obviously thank organizers for giving me an opportunity to present some of my work today, and I would say then it would be about applying correlative microscopy and spectroscopy imaging to study some functional materials, in this case, catalysts, yeah, heterogeneous catalysts. Just let's say, plan of my talk, yeah, I will introduce myself. I would also talk about motivation for this study, and also I will show you two results what we got using soft X-ray spectroscopy and also electron microscopy, and also I will come to conclusions. Sorry, summary, yeah, and acknowledgement. So essentially, I just would like to say that I'm a bit kind of, so far what I have seen the speakers, I guess my background is a bit different in sense of I'm presenting here industry. And this is also like, I guess, very important that we're actually a company who is enabling access to the synchrotron facilities. We're like a mediator, and we, help, other companies to solve their problem using like large-scale facilities, specifically synchrotrons. And this, I believe, could be also quite useful, let's say, for the Ukrainian user association, yeah, because it doesn't need to be only academic users. Yeah, it could be also industry. And what we have already seen, it's a quite powerful, obviously, there are quite powerful tools available, and actually not so many people even know about existence and what could be done. Essentially, we're Finden, we're a consultancy company. We have like around 7 people working. We're celebrating almost like an anniversary. I think it's like 10 years now, and it has all started as a spin-off from academic group. Yes, they have our, let's say, founder, Professor Andy Bill. He has developed with his colleague like a chemical imaging tomography. Chemical tomography, which quite powerful tool, and there was like a demand for it. There were some, essentially people from industry interested to apply this tool, and it's kind of naturally start to grow, and become a fully kind of independent business. Yeah, and therefore I'm saying you that we also do some obviously more conventional work, but yeah, our kind of main feature is basically what we're offering this advanced methods, which is like X-ray diffraction tomography and other kind of type of chemical tomography, based on mainly on X-ray, scattering and spectroscopy. But yeah, I'm not going to talk much about this. Actually, my work would be focused on what I have done in being in academia. Essentially, just to show you that where we're located, we're near Oxford. There is like a national lab, Rutherford Appleton Laboratory, national UK lab. And essentially, we are
like we are tenants. Yeah, we are like renting space in this, national laboratory, and it's still kind of very kind of advantageous for us because we can access lots of techniques, lots of instruments, because there it's not only synchrotron, national synchrotron diamond light source base there, but there is also neutron source, and there is also central laser facility there, and there are also lots of other things. But we actually also do use some synchrotrons across Europe. Yeah, we do use like Petra and ESRF and other instruments, as you could see. I listed here. So basically, the problem is obviously that we have this, CO pollution, and also lots of waste, specifically biomass. And idea is that, what to do with it, how to make use of it. And obviously, it goes back to like Second World War, when Germany was kind of struggling with access to crude oil, and they have developed this Fischer-Tropsch synthesis, which is essentially using like CO, like using and the hydrogen, using like syngas to generate long chain hydrocarbons, and this could be also used after as a synthetic fuel, or could be like a precursors to synthesize some useful chemicals like polymers and some other chemicals like for pharmaceutical industry, for example. And therefore the main interest of this study is this kind of type of systems. And I just want to say that here, obviously, the main focus of of this work and what I've been doing is basically correlating structure and activity in the functional material, specifically in the catalyst. And I guess all what we have seen so far today, people, synchrotron users and beamline scientists, they're obviously working in this domain, like structure activity correlation. And so basically, what how to study catalysts. Obviously, there are like two main approaches. I draw them here on the left. You can use like as I call them 0D or 1D catalysts. 1D catalyst would be like a single nanoparticle, but then you are not sure whether what you're looking at is actually really responsible for reaction happening. And this could be also like a well-defined, like a model 2D or 3D catalyst. But obviously, with the 3D catalyst, we're going to bulk, and then complexity increases. Again, it's not that easy. So, ideal system, what I'm going to say that it was like to use like a 2D flat catalyst, which are essentially nanoparticles supported on the flat single crystals. And essentially, just here a few words, how this model catalysts were prepared. So essentially, we use like some kind of polymer micelle after we added some metal salt, and we got missiles with a metal core. I mean, it was not yet metal, but it was like more like metal oxide. And after this, micelles were deposited on the flat substrate, and after calcination or plasma treatment, you end up with the essentially array of monolayer of nanoparticles deposited on this substrate. And the important thing here is that to say that actually this cobalt nanoparticles supported on refractory oxides are actually currently used in this commercial gas to liquid plants. And essentially, I was, again, looking today at this, talks, nice talks today. I kind of questioned myself, like, why, there was not many yeah, I mean, people were talking about tender, using tender X-rays or hard, X-ray spectroscopy, but, I'm here talking about soft X-rays, and some of the attendees of this meeting could, question themselves, but, what is the difference? Why, somebody using this or that? So I decided to put here the points about actually, what is the advantage of using soft X-ray compared to, tender and hard? And then I can say that it basically improved surface sensitivity. First is basically here it's average path average electron path as a function of electron energy. Yeah. So and basically what I'm trying to say here is that if we're working in soft X-rays regime, I mean here like 10 to thousands of electron volts, where exactly in this point where we kind of can probe several few nanometers of the surface of the sample. Also then LH offers like 3-5 times greater energy resolution compared to to those recorded for KH. This is like, for example, for cobalt, which is main material of our nanoparticles. So you could see that obviously LH, looking at LH will be more advantageous. And also, like LH transitions, dipole allowed compared to KH, which is dipole forbidden. Therefore, LH is more sensitive to oxidation, to spin states, and simply for some elements we just don't have edges. So we only have edges in soft X-ray range, like which is, for example, oxygen, which KH would be already 500 EVs. So, but the disadvantage obviously is that it requires ultra high vacuum, and things get a bit more complicated. But with careful thinking and planning, you could do lots of interesting things. And so here is an example of essentially of this is the sum of the results we got. So we took this nanoparticle and we put it on the two different substrates. And this is, I'm showing here like a silicon and titanium single crystal. And we could see already that, the particles behave, very different when they, after calcination and after when we have done like a redox circle, which is like reduction oxidation, which is typically used to control, to modify this catalyst, to regenerate them. Yeah, we could see the difference. And essentially, the thing that what I mainly wanted to show here, that like you could use just PIM, which is microscopy. Yeah, you get your spectra in each single point, but then you actually don't know a real size of the nanoparticles. Therefore, we are putting markers, and after measuring spectroscopic data, we are taking sample, going and putting it into the microscope and measuring there with electron microscopy exact size of the particles, how they change. And you could see here that we got, depending on the nanoparticle center or nanoparticle edge, we could see slightly different spectra, and these variations were exactly due to the oxidation state of nanoparticles, and also by doing after electron microscopy, what we have done also like helium ion beam microscopy. So we have removed partially the top layer from the sample, and we could see how the cobalt was spreading for titanium. So essentially, the main result here is that cobalt is spreading on titanium support, but it's staying kind of intact on silicon support. Yeah, and also then here another example of our work is essentially effect of oxygen vacancies of this cobalt nanoparticle structure. And what we have realized by looking in two different regions in the microscope, that the spectra we are looking slightly different, and specifically oxygen age spectra. And by looking at this A and B features, by looking at their ratio, and also by looking at the split of this A and B features, one can conclude about presence of oxygen vacancies. And as you can see, there are more vacancies present in A compared to B, because this spread here is smaller, and also the peaks are not equal. And so you can find more details. This research has been published already, so you can find more details if you're interested. But what I want to then conclude here is that we actually looked at multiple nanoparticles. So we took individual particles, we analyzed their oxygen and cobalt spectra, and we after found the same region using electron microscopy, and we measure their size, and we made we were able to see a correlation between size of the particle and the presence of oxygen vacancies and their kind of chemical state. So chemical state was different. As you can see, you have a 24 nanometer particle, 15 nanometers particle, and 8 nanometer. And interesting that this presence of oxygen vacancies actually helped to reduce the particles. Yes, so oxygen, because initially we had cobalt is obviously is oxidizing easily, at ambient conditions. Yeah, so initially we started from cobalt oxide, but as soon as we, went to ultra high vacuum, so we could already see that the small particles were easily reduced. Though the large particles, there was only partial reduction happening. But after with as you can see, after further heating the particles to 400 degrees in hydrogen, basically reducing them, helped, with this further reduction. And after we have also done exposure to the syngas. And here I want to say that we were also doing a quasi in situ experiment. Yeah, so we were. It was not possible, obviously, to do a proper in situ reaction, because in this vacuum UHV chamber for the microscope, you couldn't expose different gases and all that. So we were moving sample inside the UHV to a so-called prep chamber, where we are able to treat the sample and after move it back and measure again. And so I just wanted kind of to also say here that if there are people interested in this type of research and what could be done, using soft X-rays and electron microscopy, there are few more papers published, and this is mainly a work of Cheng Wu, who was a PhD student, and I was his course supervisor in the time where I was in University College London. So here conclusion is that we could say that this correlative microscopy spectroscopy imaging using helium ion microscopy and X-beam is a very powerful tool that this approach enabled us for the first time actually to see the evolving
elektryka, to wszystko jest możliwe. Może być taki latający grom w środku.
Sorry? Yeah, sorry, somebody probably forgot to switch his microphone. Yeah, and essentially we just look at the role of oxygen vacancies as well, and identify potential way how to actually improve the catalyst performance. And just to show here as well that we actually have been doing a quasi in situ, sorry, not ex situ, in situ experiments, and which is also enabling, more interesting kind of, studies to do. And I would like to say thank you first of all for my current employer, for people from Finden, which allow me to actually be today here with you and sharing this work, and also then, for group from UCL where I was before joining Finden. Also, actually, I want to say that I was still involved with some academic projects as well with them. So it's kind of ongoing collaboration. And also, actually, there's some work which I showed you today. Interesting enough, have been done at the Swiss light source, at the surface and interfaces microscopy beamline there. And also main results, what you have seen, they have been obtained at the IO6 X-beam beamline at diamond light source. Yeah. Thank you so much for your attention. I hope I'm
Yaroslav.
Okay on time, yeah?
Okay, the talk is open for questions, please. I just thank you for interesting view from industry, although for me still I would not say that I could not maybe get the difference. Could you say about difference of your experience as you from academy and in industry in terms of maybe roughly problems and especially how much time you spent at synchrotron or how many?
Yes, sure. Yeah. Thank you, Alexander. Yeah, I will obviously be happy to share. So I'm at Finden now already for 4 years, and we are actually, it's good to say that from point of view of access to the synchrotron, it become much more easier because we are paying for the time there. Yeah, I mean, roughly it costs like around 10,000 euros a day of measurements. Yeah, at the synchrotron. So it could be quite expensive also. And sometimes when they charge you, they not only charge for the time itself, but also it could be a time of the scientist, who was with you there, like assistants. Yeah. Some assistance from someone, and therefore I would say it's kind of good that we could basically get time very quickly, which is kind of nice. But also the thing that we also established quite good collaboration, with the people at some of the stations we're using. So we're able actually to do some commercial work, but in the meantime also to squeeze some academic work, there, though, because it's all under, we are collaborating with them. It's part of collaboration, and therefore, it works out quite well. I would say in this sense. But talking about difference, between industry and academia, obviously, industry is much more kind of much more intense and pace kind of driven environment, in sense of there could be obviously deadlines, and you actually have to be kind of more flexible and ready to adapt, to deliver on the projects. But as I say, kind of still, it's good that we are able to find some, interesting sort of, what I want to say that first of all, it's also a bit, kind of sad that when sometimes you work on the interesting project, but you couldn't really share the results because, it's a commercial work, and, you sign in this, non-disclosure agreement, so there is no way to kind of, share it publicly, but still we're able to kind of still participate in some, partnerships and academic, publicly funded projects. So, still we kind of able to do, interesting work which could be, shared publicly. Thank you.
Yeah, it's very interesting. I understand that it's quite a big topic to cover it by short answers. Therefore, I think we could discuss it somehow.
Yeah, I guess I would only suggest that my point would be like then maybe at some future meetings, what you see that there is also some, networks of these mediator companies, when obviously not the only one. There are also some, good companies like, across Europe, which also working towards, this, I guess, advertising synchron facilities, for industry. And I guess this could be like kind of also high, I would say, would be, I see there is potential to highlight it for, for Ukrainian kind of, communities, for industry related.
Yeah, thank you. I mean that for us especially interesting, because we are one of our projects which we are here. It's a scientific park, and to involve industry and so on. Therefore, it's very interesting topics for us and for me personally. So I would like to discuss it later in more detail. Yeah, I see some more questions. Anatoly, please.
Yeah, hello everyone. Thanks a lot for the presentation. I had a question which is following up a bit the question of Professor Kordyuk. So, if we talk about the commercialization of the synchrotron, so which actually Finden is excellent promoting on, do I understand it right that actually the major niche there is in the high energy synchrotron radiation rather than the soft one?
Yes, thank you, Anatoly. It's absolutely right. So our main business, what we're doing is so-called this, XRD CT, this X-ray diffraction computed tomography, and we're using like energies of 100 kV, like to penetrate, through the, quite thick, material systems, like real systems, like for example, batteries. If you take, triple A, double A batteries, and you have obviously, stainless steel case and everything. So you need to kind of be able that your signal goes through. And I have to say that it looks like the main thing, at least for us, we're using like in the hard X-ray domain.
Thank you.
Okay. I saw Luc wanted to ask something, or it's already.
And my question has been partially replayed by the previous question.
Okay, thank you. Then, if no more questions, then let's move forward. And the next speaker, Igor Bychko from Pysarjevsky Institute of Physical Chemistry, and I'm happy to have chemist here. Please, Igor.
Thank you. So, can you see my presentation?
Yeah.
So, it will be a short presentation about, I think, our requirements as chemists who work with solid materials, and in particular with in the field of heterogeneous catalysis. Actually, in some part it will be continue from as a previous speaker, Yaroslav Odarchenko. However, I think I will represent some ideas from another point of view, and it will be useful. So first of all, a few words about me and my organization. I'm a senior scientific researcher in the Institute of Physical Chemistry. It's placed in Kyiv, near the Institute of Physics and near the Institute of Physics of Semiconductors. It's the oldest institute, chemical institute in Ukraine, and one of the oldest institutes at all. Actually, catalysis and heterogeneous catalysis is one of the main fields of our institute since its organization. Founding, and at present time we have 3 departments that works in the field of heterogeneous catalysis, one department as photocatalysis, and one department that works in the electrocatalysis. So in general, when we talk about catalysis, so it's a field that combines different parts. It's a typical chemical part is the synthesis of catalysts and providing catalytic experiments when we measure the dependence of the catalytic of conversion or catalytic activity on the temperature. We investigate different chemical kinetics by variation of concentration dependence, and also we provide stability tests that are very important for industry, because in industry catalysts work in process about years, maybe 3 years. It's of course it depends. Very important part, it's a characterization of the solids, and this is actually our weak place, because characterization requires really costly equipment. It requires a lot of different types of equipment that can provide absorption methods, spectroscopies, and electron microscopies, different electron microscopy, and also a set of methods that use X-ray radiation. I will say about this later. And also we need theoretic investigations. We need specialists that can provide different DFT calculations, molecular dynamics, and can understand about band structure of solids, density of states, and some other. Generally, all catalysts can be separated on two types. It's an acid-base catalyst and catalyst for redox reactions. Acid-base, it's a typical alumina, cellulites, and resins, and some others, some such type of materials. While redox materials, it's typically metals, oxides of transition metals, maybe sulfides, maybe carbides, so this type. And here very important to mention that during chemical process, metals can be transformed into the oxides, and oxides may be transformed into the metals. And understanding what is the real state of active phase of catalyst is very important for creation an effective catalyst that is interested for industry. So reaction in this, in all cases, almost all cases, proceeds on the surface, and obtain, for example, method with very high surface is a very big problem. Actually, it's restricted due to a lot of reasons, and almost always metal-based catalysts are the catalysts with some type of support. It can be alumina, it can be silicon, it can be, for example, activated carbon. And on this support, metals deposited in the form of nanoparticles. However, it's not only nanoparticles. The main idea, the smallest particles, the higher surface area. So according to the reaction proceeds on the surface, we need surface area as large as we can create. So we need particles as small as we can create, but of course it's not so simple. So almost in all cases, catalysts are represents our atom dispersed metals on the support. It's so-called single atom catalysts. It can be clusters of metals that contain 2, 3, 10, 20 atoms of metals. It can be small nanoparticles. It can be bimetallic or 3-metallic nanoparticles. And also it can be nanoparticles of different morphology, different form, and different phase structure. So as I said, it can be particle with when part of particle is a metal, part of a particle is oxide, and another particle can be, for example, carbide. And proportion of these phases depends on the reaction conditions. So we need to understand how it works. And of course, if we talk about catalysts, it is a solid material, but it is not a solid. It's not ultimately stable solid. And reaction conditions, chemical reactions are influenced on this solid, and this leads, for example, to the sintering of catalysts. So we can create, for example, catalysts with very small nanoparticles, but during reaction, these particles are sintering with creation of large nanoparticles. It can be also poisoned by some components of the reaction mixture. It can be, for example, be covered by carbon and therefore deactivated. So to understand what is the catalyst and how it works during reaction, we need to use different methods. And here I present methods that use X-ray radiation, and these methods are also in a lot of cases presented in synchrotron facilities. The main method is very useful and very powerful. It's X-ray power diffraction, but the main disadvantage of this method is that it does not allow us to analyze materials with a small nanoparticles. For example, if we have phase with nanoparticles in the size of 2 nanometers and about this, X-ray diffraction just useful. We cannot see these particles. It's methods that use X-ray spectroscopy. I will say about this later a few words. It's also different methods such as X-ray emission spectroscopy. It's small angle X-ray scattering that is very useful, for example, for analysis of porous structure of materials. And near ambient pressure X-ray photoelectron spectroscopy, very useful method. However, the main disadvantage is that X-ray photoelectron spectroscopy XPS requires a high vacuum. So we cannot investigate our materials and our chemical processes in the conditions where these processes are provides in reality. So in XPS we need pressure about 0.1 millibars, whereas in heterogeneous catalysis typical pressures are from 1 atmosphere to 50. It can be even more. It can be even 100 atmospheres and so on. In our institute, we have very small experience in the work with equipment that have an X-ray tubes. It's only two units. It's a diffractometer and ESRF spectrometer. So, and it is really our huge problem, unfortunately. So here I want to show in more details what I mean about XRD. So X-ray diffraction allows us to investigate the phase structure of solid materials in different conditions, in different temperatures, up to, in some cases I saw it up to 1000 degrees C, using special equipment, using special equipment. So in these cases, we can see as well as evolution of materials during its preparation, and also it allows us to provide research about the evolution materials during the catalytic experiment. But as I mentioned above, I draw your attention on this, that if the active phase, and active phase it's typically metal, is size of this metal, particles of this metal is less than about 3 nanometers, we just cannot fix any phase, and XRD in these cases are unfortunately useless for us. So the one option that we have to study materials with very small nanoparticles is an X-ray adsorption spectroscopies. It's XAF-XANX. As example presented on the slides results, and here I draw your attention that these experiments, these techniques allows us to understand the distance between atoms. That is very important to understand the configuration of metal clusters. And for example, for bimetallic nanoparticles, if we use not only one metal but different metals, it also allows us to understand what is the coordination state, what is valence state of atoms or particles in the materials during the catalytic experiment. And here I draw your attention on the conditions. So this spectra was recorded during such conditions where temperature of the sample was about 250 degrees C, and pressure in the reaction cell was about 30 bars. So it is as I analyzed for today, such experiments and such loadout is typical for a lot of synchrotron facilities. And for example, if we talk about SOLARIS, as I mentioned, the beamline Astra can provide such type of experiments. I also want to show you about how it works in practice, as I found in literature. Unfortunately I didn't saw by myself, but I can only represents how it works in principle. So it's some reaction cell where catalyst is fixed in the center, and this reaction cell first of all is heated, and this reaction cell is And this sample is in the flow of different different gases or vapors, where combination of the temperature, gas mixture, and pressure, we can provide such type of experiments. And in typical case, of course, this cell also is equipped with gas analyzers of different type for providing an understanding. So how for example, activity, selectivity of catalysts is combined with this with its state. So, for example, in more reducive atmosphere where we have more hydrogen, it can be more metal in catalysts. But when we have a more oxidizer, for example, it can be CO2, we can have a more oxide phase. However, this combination phase are influences on the reaction products. And the reaction products we need to analyze using different gas analyzing techniques. So this is was the main idea that I wanted to represent, and thank you for your attention.
Thank you very much, Igor. So as far as I understand, you do not have much experience with synchrotron, right? But it's interesting.
Unfortunately, no.
Because I wanted to ask, like Yaroslav shown about escape depths, what do you think optimal? But I think it will be, we can discuss it later when you have experience already. But we should discuss actually the requirements for this beamline at SOLARIS. So it is important, but this is of course not in form of questions. Yaroslav, please.
Yeah, I just want to say, yeah, Igor, thank you so much for this excellent talk. I must say that it's probably your talk should be before mine, because you so nicely explain, you know, yes, about catalysts, what it is about, you know, how they work, and also like in terms of techniques, I guess there is better overview, and I just pick up a small thing out of it. But yeah, thank you. And then I just wanted to say that essentially also that there is like say an opportunity to collaborate, I guess, with with people from synchrotron, is just trying to build some cells there as well, so they could sometimes have a need, or they don't have specific. So I guess, yeah, what I would say, if you try to write a proposal, obviously if you want to do something more complex, like some reaction, maybe doing like in situ, actually we call it operanda, because you have like not only like in situ is typically when you do some heating and just see some transitions, but actually here you are actually doing the operanda means that something is kind of working. Yeah, there's material which is functional, and something is happening, and then you're just looking how structure is evolving, how chemistry is evolving, and it's an excellent opportunity for your work, what you showed. I mean, to find some collaborators. And I mean, the good thing that obviously what you want to do, you can approach people at the beamline, and after, if you build something, it would be like a shared, setup, shared cell, and then other users can use it as well. So it's like win-win situation here for them and for you as well. So you could, you can, and also it could be like a long-term proposal. What we have done in the past at ESRF, there was like a, I don't know whether they exist now. I mean, I guess some of the attendees now can comment. It's what's called like LTP. It's a long-term proposal. So you write a bit more, you spend more time, but instead of getting like only one beam time, yeah, which is like, yeah, what 3 days, 1 week, you get whole, you get like time for the 3 years. Yeah, you have lots of like, or a granted time, and you can plan your activity, because obviously commissioning a cell, it's much more complex. Yeah, you cannot just do something, yeah, come there, stick it there, and it will work. Yeah, assuming it will work. Obviously, it will require multiple visits. It can be long time collaboration. Just saying that, good luck with your work, and I hope to see you.
Thank you, Yaroslav. I think we just need to maybe talk separately. I think I will speak to you. It's very interesting. Maybe we will find some opportunity for collaboration. Thank you.
Surely, Igor. Yeah, we stay in touch. Yeah, surely. Yeah, just feel free to talk as well. Yeah, I would be happy.
Thank you, Yaroslav. Thank you, Igor. It's clear problem for me, an understandable problem for me. Or what you say. For us, it would be interesting also, for example, applying current to the sample and to see how it changes some composition. I think it's also similar thing. But okay, some more questions? No. Then thank you, Igor. And we switch to another speaker. Galyna Dovbeshko from Institute of Physics. I wanted to say that we moved to some biological stuff, but from point of view from Institute of Physics. Please, Galyna.
Okay, is it okay? Do you see? I don't
we
know.
see, but if you maximize, okay, now it's perfect. Yeah.
It's okay. Okay. The first I want to say thanks to organizers for invitation and the possibility to say and to tell about the problem which we have. I am from Institute of Physics of National Academy of Sciences, Ukraine, Kyiv, and from Department of Physics of Biological Systems. And we really have deals with biological system, different type. For example, here you see the cell, and it is without staining. It is tissue, and it is cancer cell. And the project which we have, and last time we was involved in different type of project, and all this project need to have spectroscopic and imaging technique. And also we want to have more resolution. I mean, spectral resolution and also space resolution. That is why I want we applied to CERIC program for the project, because we need to compare our data obtained with conventional technique with your technique, because I have no experience in synchrotron radiation technique, but during many years I want to do it. And we have with live cells, with staining cells, and you know that as usual biological system is not is transparent for visible light, and biologists and the medical people want to get images in visible light, and you see the cell without staining. It is very difficult to get it, and the people, scientists, use different application. They stain it by fluorophores, but by other type of molecules. And naturally, it is change. Sometimes it change the state of cells, and sometimes it is change the conformation. Not also comfortable, and it is proper for the cell and for getting the information which we need to get. And we try to use a different technique which does not need staining. It is coherent and Stokes Raman scattering, cars, SFG, surface frequency generation, STET, etc. And here you see it is taken from laboratory of Paras Prasart, and you can see different component of the cells without any staining. So the methods of Kars imaging give a possibility for it. We use Kars imaging during maybe 10 years with our colleagues from Lithuania and Denmark and try to get the additional information to our optical problem, to our optical technique. In our laboratory, we have TIR technique. We also use microscopy, optical microscopy from Institute of Biochemistry, with whom we involved in the different project. We have mini Raman, very good for skin, for example. And we have, it is Kars technique from Lithuania Center of Physical Research and Technology, Vilnius. And this is different cells obtained with this technique, Kars spectrum here, and also Kars imaging here without any staining. And we got some information which is interesting for us. And sometimes we need to get additional information, not enough sensitivity, not enough spectral resolution. It is also our technique used in different research which I mentioned. We also study brain and tissue and different films which is used for brain and study collagen structure in regenerated tissue. Collagen is our special interest in because it is very important protein for living body, and also it is important for diagnostics and treatment. We got many spectral markers of it, and sometimes the spectral markers not could be good result. And using technique with synchrotron radiation, if TIR spectroscopy give more resolution. That is why I tell you about our problems, and I think maybe who is interested in these problems can help us in our different studies. Now, you know that Ukraine involved in the war, and we have a lot of war-induced traumas. I mean the traumas of brain, and that is why it is very important for treatment of this trauma. And we cooperate with Neurosurgical Institute, and also involved in studying the experimental and theoretical and different model systems for better treatment of it. It is different, also different pictures obtained by confocal microscopy, sometimes without staining, sometimes with, using different approaches for it. And you see that very easy to determine what has happened after 3-6 weeks. But sometimes sometimes it is not for us not enough resolution in all this imaging, also in spectra. It is different film which used for treatment. I did not stop on it, but we got big base data on it, and it is not enough for it. Here I show the proposal number which we prepared and sent to CERIC program. It is about here using synchrotron radiation markers of cell cycle phase of model circulated metastatic cells, because metastatic cells it is one of our interesting topic according to the NFD National Fund research program. And now we study the cells, and we look for different biophysical markers of it. And using CARS technique, it is possible to say about lipid droplets in the cell without staining. And I think that additional information obtained from synchrotron radiation could be interesting and could be additional and could give more information in diagnostics of these cells. And also we involved in in other projects for derived pollution nanogrid composed of carbon-containing smoke nanoparticles and metal compounds. This project is also need to metal analysis in our model samples, but we need maybe very low concentration. That is why I ask about it. But in any case, we use nervous tissue for modeling of this process, and we use synaptosomes. Synaptosomes we use in our project, which we did before, about antiviral drugs, I mean remdesivir and the ticagrelor, which was used against antiviral, I mean in our last situation. And that is why our application to you very important. And if we can get additional information from SOLARIS, I don't know, from SOLARIS or other maybe center with radiation, synchrotron radiation, using our samples together for conventional spectroscopy and spectroscopy with more sensitivity, sometimes with more, sometimes maybe not, but it will be another view of point on our problem. So thanks for your attention. Sorry for so short maybe presentation, but I try to very shortly to say that biological molecules studying is very important using both method, conventional spectroscopy and radiation, synchrotron radiation, due to better resolution, I mean spectral resolution, and sometimes better imaging resolution and other contrast accent from my point of view. Thank you for your attention.
Thank you very much, Galyna. Yeah, I think it's a very right place to discuss, and the nephew project I think will be very helpful, and of course it is exactly the talks, actually all of talks which we wanted to have here. Please, Luc.
Thank you for your presentations. You several times mentions increasing the contrast and the resolutions, but maybe I miss actually a point. What will be the chemical elements which is actually will be important to increase the contrast in your systems, to see actually if this element has an absorption edge in the energy range of the synchrotron? So one way to increase the contrast is really to play with the absorption edge. And what will be in your systems the typical chemistry to approach? the elements.
Okay, thank you very much. I really try to maybe say about different problems. And as you mean metal, yes?
Metals or any species which is different than carbon, so to say.
But not cobalt, but I don't know, maybe cobalt also. But for example, pollution, water-derived pollution, we model with different, it is ferrum, cuprum, it is what else? It is zinc maybe, and I don't know what other element we can find in the as result of war pollutions, because we only try to fulfill this project, and I don't know. Some really, my colleague from biochemistry, they collected the samples from the war battle places, and we only to start this studying. That is why I don't know what type of element we can find in it. That is why my maybe some unsettling. Maybe uncertainly in this, but cobalt, yes, I write about cobalt. If we find cobalt, what we do if you find cobalt to apply to you?
We will at least tune the photon energy to cobalt absorption and to see contrast, absorption contrast. But yeah, I think it's going to the correct direction in the sense then we have to identify those chemistry to see to increase the contrast. But thank you.
Okay, thank you. But I did not maybe even think about this project. My project, which we presented for steric, it was connected with metastatic cells, and it was connected with maybe spectroscopy, not with imaging. It is TIR spectroscopy and resolution, I mean frequency resolution, because they have a lot of different bands, and they bands overlapped, and sometimes it is possible to get more resolution and to find maybe more resoluted bands. That is why we applied only this project. And now we involved in the war-derived air pollution. That is why it is only our first steps. That is why only here at your workshop, I thought that we can apply to this project also to community connected with this radiation. Okay, thank you very much for idea.
Thank you.
Thank you, Galyna. Thank you, Luc. Any more questions? Then let's move and switch to another speaker. Thank you. That will be Oleg Khyzhun. He is from Institute of Problems of Material Science. So we switch to physics, right? Please, Oleg.
Okay. Okay, can you see and hear me? Hello, can you?
Yeah, I can hear you, and you could just increase, make a full screen.
Yeah, I already increased.
I see in the slides mode, in many slides mode, right? It is if you see the full screen, then it is you share the different screen.
I see a full screen in my computer.
Yeah, but we don't.
Okay. What about now?
Yeah, I see the same now.
I'm sorry, I will try again.
What are you sharing? Just choose either the whole screen, your real screen, or the program, the PowerPoint.
What should I press?
What should you press? Try this пока слайдов. I do not see your mouse, actually. It's hard to... Yeah, actually, we can live with this because
maybe we can live.
Yeah, we can live with this. Just then close. You can increase a bit. You can zoom it a bit. It will be better. But
okay. First of all, I want to thank organizers of the workshop for inviting me and to give possibility to present some results on exploring electronic structure of some oxygen and transition metal bearing components with application of both laboratory source and synchrotron radiation. I would like to start with I would like to stress that some transition metal oxide like molybdenum and tungsten oxide.
Oleg, if you switch the pages, you're still on the first page. Is that correct?
I switched it now, and on the second one, maybe.
No, you see, if you want to use this screen, just switch off the presentation and just use this multiple, how it's called, multiple screen, multiple pages. Just press by mouse.
I don't know what should I do.
It is the same. Just do not start slideshow. Don't start slideshow. Just go in this way, like this. Okay, like this. Yeah.
You can see the second file.
Okay. Now I see the second slide, right?
Okay, I'm very sorry.
No problem.
I have problems with the presentation, and I don't know the main reason of such problems. So I would like to say that I want to present some results of studies of transition metal oxides. They are very interesting for practical use. For example, molybdenum and tungsten oxides are very famous for as a phenomena of photochromism and electrochromism, and such features are origin of either ion incorporation or non-stoichiometry, And electrochromism and photochromism are widely used in practice, for example, for high contrast displays, variable reflectance mirrors, smart windows. They are widely used in catalytic and photocatalytic reactions, and substoichiometry of such oxide can be made by exposure to atomic hydrogen radiation with different beams of ions or electrons heating in a vacuum, and also some oxides like molybdenum and vanadium oxides reveal formation of a number of the so-called magnetic phases. In this talk, I would like to give some results on changes of the electronic structure in the case of formation of some vacancies and changes of the crystal structure. We use generally in our work, we use three main experimental techniques. In fact, X-ray photoelectron spectroscopy, XPS, using either generally applied excitation with magnesium or aluminum laboratory sources, or synchrotron excitation. We use either possibilities of base 2 in Berlin or delta in Dortmund, and also X-ray emission spectroscopy with electron band or photon source, and also synchrotron radiation is applied, and X-ray absorption spectroscopy employing both laboratory and synchrotron excitations. Combination of such three experimental technique gives possibility to probe total density of states and partial densities of states in valence band, as well as possibility to investigate energy distribution of the unoccupied electronic state in the conduction band. And experimental data are verified employing theoretical techniques. We employed again 2K program and method are based on DFT. Advantages of synchrotron radiation. Sometimes we have very small samples that cannot be studied employing laboratory sources. Sometimes some spectra cannot be excited with laboratory sources, and application of synchrotron radiation gives possibility to depth profile investigation. They decrease in several orders of magnitude accumulation times. High energy resolution spectra can be derived, and possibility of measurement resonant X-ray emission spectra. Here results of studies of molybdenum oxides. You can see variation of XPF spectra with changing of energy of excitation, and here you can see changes of the spectra when they go from molybdenum oxide to molybdenum bronze and molybdenum cubic molybdenum dioxide. In molybdenum 3 oxide, we detect only one energy state, chat state of molybdenum, while in the bronze and molybdenum dioxide, 3 kinds of molybdenum chat states can be resolved. Formation of near-Fermi subband in the case of molybdenum bronze and molybdenum dioxide was studied using deft calculations, and we can state that this subband is formed by molybdenum 3D 4D states in the case of molybdenum dioxide, and both oxidant 2P and molybdenum D states in the case of molybdenum bronze. Here you can see that when going from a cubic molybdenum bronze to molybdenum dioxide, we observed complete elimination of the O2P bands as realized based on NextSAF's order or 1S spectrum. We studied experimentally and theoretically electronic structure of cubic molybdenum dioxide and found good agreement between theory and experiments. Here you can see that the main input in the near-Fermi subband comes from molybdenum EG states, and as you can see from comparison of total dose and partial oxidant 2P states, the main contribution to valence band comes from oxidant 2P states. Here, result of studies of tungsten, 3 science and non-stoichiometric hexagonal components when going from 3 oxide to non-stoichiometric oxide, we detect formation again this near-Fermi subband. Here you can see that when normalizing on one and the same integral intensity of the inner tungsten 4F spectrum, you can see increasing intensity, relative intensity of the valence band with increasing number of vacancies in such a case. Here you can see a result of studies of X-ray absorption spectra, and such studies can be applied for evaluation of changes of the effective charge on tungsten atoms. You see linear changes of positive charge on tungsten atoms. Here results of studies of chat state of tungsten atoms when in the case of studies of hydrogen bronze and hexagonal components. Results of comparative studies of hexagonal and monoclinic, usual form is monoclinic, and hexagonal form is a special tunnel like crystal structure of tungsten trioxide. You can see that when going from monoclinic to hexagonal, irrespective of stoichiometry, you can see broadening of the spectra, both X-ray emission and XPS spectra. Here, when you compare on one and the same energy scale, XPS spectra and X-ray emission spectra associated with oxygen, you can see that the main contribution at the top of the valence band comes from O2P states, which is in accordance with theoretical expectations. On this slide, I would like to present you result of studies of the so kind hybrid nanostructures. We prepared nanorods of molybdenum trioxide, and then these nanorods were treated with organic substances like pyrazine and dipyridine. And after calcination at 400 degrees, we were able to synthesize well-defined molybdenum trioxide crystals. Very perfect crystal structure and quality was confirmed by high resolution transmission electron microscopy, SAT pictures, as well as this is schematic drawing explaining formation of such single crystals. And this results of verification of the electronic structure using both XPS and X-ray emission spectroscopy techniques.
Oleg, may I ask you to be not so details, because we are already too late with time.
I need only a few minutes.
Sure.
I would like to say that similar data were derived employing dipyridine, and also we tried to receive such result using other nanoparticles, for example, chromium oxide. Nevertheless, we could not receive single crystals in such a case. And here I would like to show application of synchrotron radiation for resonant inelastic X-ray scattering spectra. First of all, we start with measurement of Nexus spectra, and we should find some special energies of excitation, and then we measure X-ray emission spectra, applying this specific energies for excitation. And here you can see changes of the shape of spectra when you change excitation, and such application of synchrotron radiation allows to define position of the so-called charge transfer bands in the case of vanadium oxide. And here I would like to show you results of studies of depth profile spectra. We measured since penetration of the energy of the depth mean pulse electron depends on energy of excitation, we measured at different temperatures and different energies of excitation. And this electronic structure of such oxides characterized by two different kinds of oxidant atoms, vanadilyl and bridging atoms. And we tried to define the average reduction degree, and our results indicate that the maximum average reduction degree corresponds to about 75 Kelvin. And I would like to shorten. I would like to acknowledge my colleague from different universities that give possibility to carry out synchrotron radiation measurement and supply these samples. And thank you for your attention, and I'm sorry for some problems with presentation.
Thank you for the talk. With questions? What are you feeling about this actually beamline imaging? Which the most interesting problem?
Sasha, do you mean Solaris?
I mean, which we are building at Solaris, which we plan to build at Solaris.
I would be happy to work on this beamline because it is exactly suited for task we used to do, because it allows to use soft X-ray and partly beginning on the heart X-ray, so it covers the most interesting electron energies. It allows to use for almost off of transition metal light elements, 4D elements. I don't know with respect to heavy elements like 5D, but for very mostly used elements which compose of most interesting samples, they suit very well. So it would be very good to work on this using these possibilities.
Okay, good. Thank you, Oleg. And then we move to the last speaker. And it will be Andrii Goriachko from Taras Shevchenko National University of Kyiv. Are you here, Andrii?
Yes, okay. Hello.
Okay.
So maybe first the previous speaker has to switch off his presentation.
Yes, Oleg, could you stop sharing?
Okay. Okay. So let me try to share my screen. Okay. Do you see my screen now?
Not yet.
And well, it says it's shared. Is there anything?
No, it's just written that you started screen sharing, but I do not see.
Yes, I started screen sharing.
I just see black screen.
Oh, this is, wait a second. So maybe let's try again.
What are you sharing?
Yes, I'm just sharing my presentation.
Share your screen.
This is what I'm doing.
You can share either presentation or screen. Which window are you sharing?
No, I'm just sharing my screen, the portion of my screen where the presentation is. But something happened.
Portion.
I don't know what's the problem. Yeah, there are. I think. And then everything disappeared. Alexander, do you hear me? Maybe the best way would be if I can send you my presentation by email and you will simply feed it in. Can we do it like this?
Yeah, we can.
I think this will be, because something is not working. Just a second.
I will stop your sharing then.
Yes, you can stop because obviously it's not working.
Yeah, you can send it me and try it once more. Just choose different options. You can choose either sharing screen or share this window of your program.
Yes, I did it all right now, but obviously it hasn't worked. So just a moment, let me just find your email. I am very okay. So here's your email. I am attaching the file. Okay, so I just sent you my PDF file, my presentation, and hello.
Yeah, I'm still waiting. There is it is now often slow. Goes. Okay, I see. Good.
Yeah, so if you'll be so kind to project it onto the screen, and I will start my talk, and I will say next page, and if I say next page, then you switch to the next page, and in this way we can make my talk. I'm sorry that something is also not working with my computer. Okay, so yes. So I'm starting, yes. So today I will talk about graphene on germanium 111. And it's about growth, electronic and structural properties, and mostly important about perspective applications. Next. So currently there are a lot of proposals to utilize this system where graphene contacts germanium substrate for numerous perspective electronic devices with various unique properties. For example, the most common electronic device, transistor, is already being considered that it can gain a lot if graphene is utilized within its structure. And there are actually quite a lot of proposals. I will just show you a couple of several very recent papers, like the ones that you see here on the screen. So here you see the heterojunction transistor. It's a bipolar transistor which contains graphene as a base electrode. And here on top, on the right, you can actually see the structure of this transistor. Next one. And there are also various different varieties of transistors that you can make. For example, hot electron transistors, the structure of which and the photo of which you can also see on the screen. It is also a very recent publication of the authors that you see here. And in these terms, you can actually, if you look at the analogy in the vacuum electronics, then for instance, in this case, you can consider graphene so that it can be viewed as playing the same role as a metal grid in the vacuum triad. Next, please. Then graphene also makes a perfect passivation of the germanium surface, which can be applied to create stable heterostructure devices, stable in terms of the influences of various environmental factors. Next, please. And of course, since we all know that graphene is a very nice conductor, we can also imagine a Schottky junction, a Schottky barrier. And there were also proposals and very recent publications about the interface between germanium and the single layer graphene, which is a Schottky junction, the band diagram of which you can also see on the screen. And also it is important that in this context, you can, graphene here can be viewed as a metal electrode, which is just one atom thick, but is also optically transparent, which can be of great importance. You can utilize it in creating various, for instance, photoelectric sensors as a transparent electrode. Next, please. So this is the type of the deposition process, which is applied quite often by many researchers. Graphene is usually grown on copper substrate. Then it is attached to the PMMA film and detached from the substrate and then transferred onto germanium. And once the PMMA is dissolved, you are basically left with graphene on germanium substrate. However, of course, such procedures, these are procedures at ambient conditions or wet chemistry procedures. And of course, the germanium substrate is not atomically clean under the graphene layer in this case. Next, please. So what I have studied so far, but without synchrotron radiation, just with small lab-based techniques like scanning tunneling microscopy and also electron spectroscopy, was the CVD type, chemical vapor deposition type of graphene germanium interfaces. In which case, of course, germanium substrate is first achieved in the atomically clean state. And then, as you can see here, there are STM images and corresponding OSHA spectra showing two situations, atomically clean germanium substrate that is on top, and germanium substrate partially covered by graphene. And this is a spectrum and an image on the bottom. So basically here you see that there is a substrate with atomically flat terraces separated by single atomic steps. And some of them are covered by a certain structure, which you can see in a detail in the inset. And as it turned out, this is how the graphene flakes look like under the scanning tunneling microscope in ultra-high vacuum. Next, please. So if we zoom in, we again can compare the atomically clean germanium substrate that is on the left and partially covered by graphene flakes that is in the middle. And of course, there is no such thing as absolutely atomically pure substrate or whatever, any kind of material in nature. So there are always some kind of impurities. Carbon is a very common impurity when you prepare the semiconductor surface like silicon or germanium. And you can see here that we consider that the surface is atomically clean, but still that means it's clean to a certain extent. There are some impurities, they can still be present on the surface. And for instance, on the left side, you can see that when there are two very small amount of carbon atoms, then they just form the C letter, as you can see in the lower part of the image, which tells us that this is carbon. But when there are a lot of carbon atoms, then they form a continuous graphene layer, as you can see in the middle image on the slide now. And so basically this is how it looks like also in the STM with atomic resolution at high magnification. Next, please. Also, I have made experiments at different, although low energies, low electron energies, that is obtaining spectral microscopic scanning tunneling microscopy experiment or observation. And here we indeed have been able to confirm that yes, the graphene layer can act as a sort of analogy to the grid of the vacuum triad. So in some situations, for some electron energies, they can tunnel through, or some of them just tunnel into it. And we have been able to tell this difference by means of being able or not being able of observing the substrate germanium atoms in the STM images of the germanium substrate covered by the graphene layer. Next, please. And so by this, I actually want to conclude saying that this system, graphene on germanium, is a very interesting system with a lot of perspective applications, but it was not investigated using the synchrotron light. And from the previous slides, I think it is obvious that the issues that can be investigated using the synchrotron-based techniques would be, for instance, lateral homogeneity of the coverage, because a lot of images that I have shown you, they show non-uniform coverage of graphene substrate, of germanium substrate by graphene. So there are covered areas, and not uncovered areas. And of course, chemical bonding at the interface will also be very interesting, also in terms of the depth resolution, which is, of course, very easily doable by means of the synchrotron-based photoelectron spectroscopy, for example, or adsorption spectroscopy. So it will be extremely interesting to see, to distinguish the bonding just within the very few layers, or within the upper layer, atomic layer of this system, of this interface. But of course, it will require also spatial resolution at the nanoscale to differentiate between the covered and uncovered areas of the germanium substrate. So this is also where we can benefit from the synchrotron-based techniques. And of course, ultraviolet photoelectron spectroscopy, as you can see, these two images, where a big graphene flake is situated on the germanium substrate, again, partially covered. It has the STM image which changes in real time. That is, it differs when you observe it from one image to the other. And that means that the electronic structure and perhaps the crystalline structure as well at the interface is changing in the real time. So observing this would require also the temporal resolution in the maybe seconds or sub-seconds range. And so I think by this I will conclude my talk, and thank you for your attention, and I will be happy to answer any of your questions.
Thank you, Andrii. Okay, it is the last talk. I think the next session will not be long. Therefore, in principle, you can ask a question. If you're waiting for questions from others, okay. Better Yaroslav. Yaroslav, please ask questions.
Thank you, Andrii. Yeah, thank you for nice talk. Obviously, my question then would be: could you please be more specific, unless maybe I overheard or I missed it? If you would be offered now, to go and do any kind of analysis, like a synchrotron-based type of analysis, what you would go for? Yeah, what would be, the most useful for you? What do you think to better kind of understand this system and to, yeah?
Okay, I think what I would be interested to do right away would be the specially resolved photoelectron spectroscopy. That is where I can see the chemical bonding information, and also specifically at the uppermost layer, so that is between carbon atoms, between carbon atoms and germanium atoms. So this is the most obvious thing. We will need a resolution, as you can see, for instance, from the image now on the screen. We would need maybe also the spatial resolution. That's why I talk about spectral microscopy, photoelectron spectral microscopy, within maybe tens of nanometers to differentiate, to see the mapping. Because if we are speaking about the applications of such graphene layers on germanium in electronic devices, and obviously we need to achieve the situation when there is a homogeneous, absolutely uniform coverage without any such holes, as you can see here on the screen, where there's uncovered germanium. So this should not be the case. And therefore, the growth conditions have to be checked during such experiments. So, as I say, I will repeat, spatial resolved X-ray photoelectron spectroscopy. That would be my first choice.
Okay, thank you. Yeah, makes sense. Yeah.
Okay.
I would say that it would be interesting. Sorry, you didn't finish yet. Yeah.
No, I said that it's all makes sense, and yeah, I said that he definitely should apply them. Yeah, should try to get some time.
Okay. Thank you.
My impression, if speaking about the beamline which we are planning, that the diffraction with localized beam would be interesting for you, but now applying for ARPES, angular resolved photoemission spectroscopy, to SOLARIS, I think Eva could actually not help, but say answer your requirements. But you should just apply for beam time.
Okay, thank you.
I wanted to ask some maybe naive questions. I have an opportunity to switch it. Yeah, what could you just explain what is this? What makes this honeycomb structure, and what are these white dots? because I'm lost.
Yes, I understand. So when graphene contacts germanium in atomically clean state, then we have a very close contact of two lattices. One is the surface lattice of germanium, another of graphene, and they have different
superstructure.
Yes, yeah, sure. So this is a kind of a so as a result, the upper layer, the graphene layer, becomes corrugated. Yeah, it's basically like when you are trying to fit a carpet, to put the carpet on the floor of the room, but the size, for instance, the size of the carpet is larger than the room, so it will have to be corrugated in order to fit. So this is a kind of a phenomenon that we are dealing, and it is best seen in the empty electronic states, and that is the leftmost and uppermost image that you can see on the screen now. So you can see the height corrugation. But then at other energies of the tunneling electrons, it can be that some of them tunnel into the graphene, because there are electronic states available for this. And in other situations, for other energies, they tunnel right into the substrate because there are no electronic states, or the probability of tunneling is too low. And these two phenomena, they give rise to all other images that you can see on the, and it's indeed so that it's easy to get lost here. However, maybe the uppermost and rightmost image, the image D, explains the point. At image D, you can see there are some remaining brighter spots. These are some remaining spots within the graphene layer, which are actually imaged in the STM. And in between them, there are a lot of smaller circles, and these are just the germanium atoms. So we have checked that the periodicity, the distance, the interatomic distance in between them is in D, image D. The interatomic distance between them is is just typical for the germanium substrate. So that means in this case, we just see through the graphene layer very nicely, and all the other images are situations in between. Yeah. Also, there are at plus volts. So if you have positive voltage, then these are the empty electronic states of the sample. That is of the substrate and of the graphene together. And negative voltages, for example, F and G, occupied states.
I understand. Yeah, that the dots which you see on D, it is just. Okay, this is ordered. Yeah, either it is graphene or it is beneath graphene. It is another question. And black stuff, it is just superstructure. It is superstructure like Moir pattern. Yeah.
Yes, sure. You always see some remaining.
But on G, this random, let's say, random white dots. What are they?
Well, it's a very nice question, up to the point. Thank you very much. Let me be honest. The honest answer, we don't know yet. To do this, one would need to do extensive theoretical modeling of the STM image formation for the known geometrically known crystalline structure of the interface. However, my proposal, so my idea is that this in image G, these brighter dots, these are still carbon atoms of the graphene layer. However, as you can see, the carbon atoms within the graphene layer becomes non-equivalent. So some of them are brighter, some of them are almost not visible. And also, it is proposed, but not proven, that the reason behind this is that the layer of germanium atoms just beneath the graphene is actually mobile at room temperature. So that means there are a lot of vacancies, and as a result, there are a lot of configurations of the germanium atoms in the topmost germanium layer that they can assume, and by this they change the local geometrical structure of the interface and the electronic and the local electronic structure also as a result. And as a result, some of the carbon atoms in the occupied states become brighter. So they start to have more local electronic density of occupied states due to this. Okay, this is my answer.
Okay. There is such a hypothesis. I understood. Thank you. More questions to the last speaker? Okay, then I should thanks all the speakers of this session again. I will stop sharing.
Thank you.
And we just go to the last session. Jakub wrote me that Eva will
yes. So unfortunately, Jakub asked me to apologize for his absence because he has been called for urgent task and he cannot join the closing session. And therefore, I would like to, on behalf of Jakub and the organizing committee, to thank you for attending the second edition of Light for Ukraine workshop. It was a great pleasure to host all of you. And we are looking forward to further cooperation. And Sasha, now I will pass the floor to you.
Okay. Thank you, Eva. I just wanted to say first, that I'm happy that was a successful workshop, but at least I like it. In a sense, it was very interesting to see the examples of the beamlines and their tasks which they are solving on the topic which we plan to build at Solaris. So it was very instructive and for me also, and I think for other people. As for the last session, and I think it was successful in a sense, we didn't choose. It's not very selected. It almost a random selection of the people who was just ready to present and some results and interested in this beamline. This just shows, I would say, that quite big potential of people in here, because I think we have, I'm sure we have much more people who are interested in it in very different areas in this sense. And I would say that we are ready I mean that we have this consensus, like that we have from European colleagues, from Solaris people, from LIPS, we have requests. They want to help for our community, for our synchrotron user community to grow and this nephew project will be directed to this. But from our side, I mean now from my side, or from people who are in Ukraine and who are have some experience with synchrotron measurements, we welcome people who want to start to do synchrotron research. And the first thing, it is just suggestion just to apply for beam time. And just if you need any help in preparation of these proposals, just write me and other people, and we will distribute, try to help you as much as possible to suggest where to apply, and just to distribute your questions where to apply to other people, to European colleagues. They will help, and just to start to do it, just we need, and you need to start to do it, right? Because it's usually takes time and needs some experience to apply for the beamlines. So this is actually all what I wanted to say about this workshop. And from my side, I would like to thank organizers for a very good job. I see that it is organized perfectly from your side, and all this Zoom connections and the program very nice, very nicely organized. This is from my side, and still we planned this last session like discussion and just answering the more general questions. Therefore, it is I'm not finishing it. It is just I expressed my gratitude to organizers, and just please, if you have any questions, this is a good time to ask. Actually, I'm saying we will try to duplicate this information, but this is public information about the deadlines of this submission of the proposals to beam time. And for Solaris, when the next it is in March, I think. Yeah, the next.
So the next call begins in March, on the 1st March.
First March. Okay. It begins, or it is deadline to apply.
This is just the beginning. So until the end of March. So you have 4 weeks.
Okay. Yeah. 4 weeks. Okay. Just I think it would be nice because it is like Jakub said, it is not only that we are building, we plan to build this beamline and for using at Solaris, but I would say that more important to build cooperation with Solaris in this sense, and just I invite you to suggest to apply for this for other beamlines at SOLARIS Centre. It will be very important experience. Okay, as far as I understand it, you will have this recording and we can make them available then, right? It is, Eva, do you know about this?
Yes, I think this is correct. Yes, this is correct.
Yeah. Okay, thank you then. If there is no questions, then thank you and see you next time. The microphone is
okay. My microphone. I just want to thank you, Sasha, for the great cooperation. Again, for the great cooperation. It is really a pleasure to work on workshop with you.
Thank you, Eva. Bye bye. Then.
Bye.
Thanks. Goodbye.